Ага. Всё. Давай, у тебя там флешка или что? Ага. Так. Ага. Стримит, вот видишь. Ну я просто, знаешь, без камеры, просто экран. Презентации голос. Правда, единственное, что качество вот даже презентации, надо там скорости не
Вот
хватает.
PDF-ка, вот это вот.
Вот это, да?
Да.
Ага. Сейчас сначала. Алло. Так, сейчас. Так, сейчас.
Слушай, давай, знаешь, еще пока народ собирается, может быть, эту рыночную заявку там надо подписать.
Ну, давай потом. Сейчас,
Потом?
да.
Ну ладно.
Да, я просто ничего не распечатал.
Ну ладно.
Сейчас я распечатаю. Так. Угу. Сейчас он разогреется немножко будет. Il s'échauffe.
Hein?
J'ai dit il s'échauffe. Le projecteur, tu vois. Угу. Morning. Привет. Так. Ага. Non.
Rien à signaler.
Tiens. C'est académicien.
Ouais.
Oui, mais je... Mais je suis... Okay, good morning. So we are starting the second day of our workshop, and the next speaker is Sergey Kovalev from Computer Science, from Institute for Control Sciences, and he will talk us about computational fracture mechanics. За компьютер садись, чтобы переключать.
Okay, computational fracture mechanics. My talk overviews some current issues and aspects regarding in the relatively modern field of computational physics, specifically computational fracture mechanics. The problem domain of computational fracture mechanics is deals with stresses and cracks, which are ubiquitous in various structures. It is known from hard practice that any construction built from any material, if put under certain stress, sooner or later will break, and the cracks will emerge seemingly spontaneously, and cracks will grow and grow as so far as to completely break the construction. And there are a number of examples, such as planes, hydroelectric stations, etc. buildings. The basic problems which are addressed by fracture mechanics are as follows. First question is, what is the residual strength as a function of crack size? That is, as soon as cracks are inevitable, we always need to know how long will the construction remain whole and capable to perform its function in presence of cracks. And it is generally obvious that the larger is the crack, the smaller is the strength, but the exact relation between these quantities is sometimes crucial when the various repair procedures are scheduled. Another question is, what is the critical crack size, meaning that the size at which the complete failure occurs and break and the construction actually broke. And the next question is, how long does it take for a crack to grow from a certain initial size to the critical size? That is, this again is important for service, maintenance, or disposal procedures, since it is needed to know the amount of time during which the crack will grow to the critical size. So basically, as can be seen from the basic curves, for example, the first curve here shows the dependence of crack size on the amount of time or an amount of work cycles of the construction. Here, the difference here, actually, two arrows, means that basically there are two major kinds of fracture processes. The first one is a break, when the stress is constant and or increasing in time, and the construction evolves steadily to break. And another kind of fracture process is so-called fatigue, when there is a periodic applying of some load, some stress, and then removing it. some kind of cycles occur, and with this in this process, the dynamics of cracks is usually different, and sometimes it's it is interesting that sometimes the periodic pressure applying periodic applying of stress leads to more fast breaking of the construction, and in other conditions it can lead to lower, to slower going to break. Yet generally the crack size depends on the on time or on the number of cycles, just as shown as the curve, and as soon as the critical crack size occurs, then failure occur, and construct basically no longer exists. This may be considered as a kind of phase transitions, such as, for example, melting an ice to water. And later we will see how this analogy is explored in certain physical models. But generally and basically, what the conditions of failure and strength is measured in times of the tension, in terms of tension. That is the quantitative value which shows the amount of strength of the construct of the construction, and with various functions depending on geometry of the construct, depending on the properties of material from which the construct is built. The estimations of critical parameters, such as critical crack size, are given in terms of by the using the methods of fracture mechanics. Actually, the fracture mechanics is under development for more than 100 years, and by and large, it is based on energetic considerations. That is, the overall model, the general model, the concept of occurring and growing the cracks is based on a rather simple observation that stress or strain, when applied to the construct, actually pumps in some kind of energy to the material, and this a crack is precisely a way for this energy to go away, since it cannot be, since it is imagined that the material cannot accumulate the infinite amount of energy, and as soon as the energy is pumped into it via stress, strain, either constant or periodic, then sooner or later this energy have to give way out, and it does so by producing cracks and eventually breaking the construct, the construction. And so the more or less trivial, more or less obvious overall estimations of the amount of work which is pumped into the construction is shown in the slide. The generally basic algebraic formula which allows to estimate, allows for rough estimations of answers to questions which I listed above. That is, it shows when that is to say, basically the formula in the yellow square shows that how much energy can be pumped to the construction in the form of linear bar to produce cracks in it. One of the interesting questions, specific question, actually the problem with the estimations like shown in the yellow square is that they are quite sometimes too simplified, and they can allow to predict the time of break or the stress needed to break, as they say, with precision of an order, but actually the actual break can occur, for example, twice as fast as the rough estimation predicts, or twice as longer as it predicts. That is to say, for practical needs, much more precise estimations of the crack sizes, crack growth processes, and break process are needed. And here different, and it occurred that actually the criteria, the specific estimation often depends on the model with which we describe the geometry of the crack. For example, at the left picture, left square on this slide, we see actually the simplest estimation given assuming that the crack is linear. That is, this doesn't mean that the differential equations which describe the evolution of crack are linear. Not at all. These equations are nonlinear always, but the geometry of the crack is assumed to be just a straight line, and given this assumption, we basically calculate the amount of energy needed for the crack to linearly grow by solid lines in the directions of solid lines, and we have the from this we have the critical amount of energy, which is given on the square in the lower side of the slide. And this is basically the reformulation, maybe in another terms, of the estimations, which of the rough estimations which were shown on the previous slide, and which are known to be just too rough, too approximate for practical use. So a number of models with more difficult, more realistic, that is to say, geometries, more realistic shapes of cracks were suggested. For example, in the center of the slide, the model is shown where the crack is modeled as a broken line, and it has the range between its beginning and the end is marked as L0, while the proper length along the line is L, which is generally bigger, or can be sensibly bigger than L0, and taking into account this difference between the range and the proper length of the line, we get different, more different, sometimes more precise amount, more precise estimation of the critical energy needed to break the construction. But even more elaborated crack geometry models suggest it to consider to be fractal, and it is it can be supported by the our everyday life observations that actually the cracks are very extremely, as they say, tangled in geometry, and they are not just they are usually never straight lines, and very seldom they are just broken lines. Actually, they are they usually just cover the piece of the surface of the construct to be just near breaking quite completely, just so as can be mathematically modeled by a fractal. And with this, as you maybe remember, the fractal line basically can be produced from the broken line by a kind of limit to when the proper length of the line goes to infinity. Actually, it is a broken line which is broken at its every point and therefore has an infinite length. And so essentially the fractal fracture covers a certain amount of square of the surface, and it is characterized by such geometric parameters as Hurst parameter H and characteristic width L small 0. And we see that calculating the amount of energy needed for a crack to grow along this fractal geometry, this fractal shape, is given at the formula below, where we see that comparing to the estimation obtained in the under hypothesis of linear crack, we see that there is a certain geometric factor which which for non-trivial fractal geometry can give significant difference to the value of the crack energy, and it is indeed shown by different experiments that the fractal description of fractal model of crack produces more precise estimations of critical energy and of crack propagation and break processes than simple linear model. But currently in the present stage of engineering, it is not enough to consider these models as described above, not just because we have limited precision of crack geometry, etc. Actually, current stage of engineering imposes more dimensions or more factors that complicate the fracture mechanics problems. Namely, the contemporary fracture mechanics problem has to be multi-criteria, meaning that they involve comparative analysis of different crack propagation criteria based on different conceptual and physical models of failure. And basically, the example of linear versus fractal crack geometry is an example of such approach, and there are a number of other conceptual and physical models which has to be taken into account and has to be estimated according to their applicability and the predictions regarding the break which they provide have to be compared with each other, and the most appropriate has to be chosen. Then the multi-criteria is not the single factor that complicates the fracture mechanics problems. Another factor is multi-scaling. That is, it is required to coherently model crack initiation and impact across all scales of the product, starting from the microscopic scale in the at the level of specific molecular or nanoparticles with which the material is construction material is assembled, and then the model of crack shell has to be smoothly, coherently transferred to mesoscale. That is to say micromillimeter scale, and then to macro scale, to the amount of constructed all, and actually even further it has to be continued further to the large system in which the considered the construction under consideration is just an element, so that from the microscopic level up to the system level, the coherent modeling is required. Another factor is the need for multiphysical analysis. That is, the Rakin effects need to be examined that are jointly caused by mechanical forces, gravitation, heat, electromagnetic fields, and chemical reactions. That is to say, consider, for example, a nuclear reactor. For nuclear reactor, we cannot, when we consider the possible scenarios of crack propagation and break of the nuclear reactor, we cannot say that the cracks are caused only by mechanical force, or solely by gravitation, or solely by heat. Actually, the processes which take place in the reactor is inherently multiphysical, and it is the mutual influence of mechanics, gravitation, heat, electromagnetism, and chemistry that actually produces cracks. Actually, as we said, pumped energy into the nuclear reactor construction, and eventually causes the cracks and break. And
it's not energy in usual sense. It's kind of special parameter for this theory, or it's just usual energy.
It is a form of energy which is as they say, which takes the form of strain or stress in the piece of material, and that eventually gives way out in the form of crack. This is on the microscopic level. It is usually accepted that this energy has electromagnetic nature. That is, it is a kind of tension between atoms or molecular, which are on the scales at which electromagnetic forces work. That is, as soon as we consider the four basic forces, that is gravitational, electromagnetic, strong and weak, then the strain energy which produces cracks are definitely electromagnetic energy, but on the mesoscopic level, on the level of the small cracks, micrometers or millimeters long, its energy manifests itself rather differently than, for example, the energy of a battery, although it has electromagnetic nature on microscopic level. So we can say that the strain energy is a specific mesoscopic form of the microscopic electromagnetic energy. And the kind of, as I said, the kind of phase transition, just as soon as a piece of ice accumulates heat energy, just as until phase transition occurs and it turns into water, just roughly similar, in similar case, the solid construction accumulates stress energy in electromagnetic, specific electromagnetic form up until it gives out and breaks to pieces. And that's the basic conceptual model of fracture mechanics. But as I said, the initial streams of energy, which is converted into strain energy and then eventually gives way to cracks, are generated by different, entirely different physical influences, such as I said, mechanics, gravitation, heat, etc. Then, and one more factor which makes live of fracture mechanics difficult is that it is needed to consider multi-material constructions, which are that is the fracture mechanics has to be applied to products made from composite materials or highly heterogeneous structures produced by additive 3D printing technologies. That is, currently we can see that actually very small amount of very small piece, small fraction of materials are fraction of constructions are built from the homogeneous material. Are very such as even the classical materials such as wood or concrete or brick are definitely not homogeneous. They built from quite a mixture of various particles of various sizes, and so the homogeneous, so the models of crack propagation in homogeneous materials often simply doesn't apply. For example, it is obvious from the everyday experience that if you have, for example, in a concrete, you have a piece of stone in a mass of concrete, then the crack is quite usually will occur somewhere around the boundary between the rock, the stone, and the enclosing concrete mass, and these heterogeneities has to be considered, has to be taken into account when modeling crack initiation and propagation and estimating the parameters of the construction with regard to possible break. Needless to say that in presence of all these factors, it is just impossible to solve the problems analytically. It is not possible to draw a formula, however complex, that will describe, for example, the amount of time remaining to failure as a function of a number of parameters such as listed there, simply because these parameters often are very difficult to represent quantitatively, not to mean to measure, to obtain, to aggregate to larger parameter, etc. The only way to go is to imply computers, so to develop computational fracture, computational approaches to resolve the fracture mechanics problems. And indeed, during 1970s, the computational approaches, computational methods of fracture mechanics are under steady development. The basic idea is based on the method which is known also since 1970s, and which is actually the most widely used method of solving mathematical physics problem on computers. That is so-called finite element method, or FEM. Finite element method assumes that it basically suggests to split our construction, our geometry, the geometrical model of our construction, to small polygons or polyhedra in three-dimensional case. And these polyhedra are assumed small enough that within each polyhedra, the behavior of our physical field or process is strictly linear. So it is possible to give the linear estimation of the, for example, of the tension of some physical field on each polygon, and then propagate from one polygon to computationally, I mean, propagate from one polygon or polyhedra to the adjacent ones just by the requirement of continuity, which gives algebraic linear equations. So, in a sense, that the set of polygons or polyhedra into which the geometric model of the body is split is called mesh, and the whole computation of some physical field at this mesh is reduced to solving very big system, very large system of algebraic linear equations. And since there are very wide spectrum of algorithms to numerically solve linear expressions, linear systems of linear equations, so this explains why finite element method is so widely used in modern computer-aided design and analysis tools. But when applied to the specific problems of fracture mechanics, that is to crack initiation propagation, it was suggested to introduce so-called double nodes at the crack edges. So it is if you imagine a mesh which splits some solid body, then a crack in the this mesh basically leads to certain kind of doubling nodes which are adjusted to the crack, and as crack grows, the remeshing has to occur. That is, mesh has to build. Has to be adjusted, has to be built differently, just in order to follow the change of geometry initiated by the crack. And
it's more or less like numerical integration, right?
At stable, that is static. In static case, it is a numerical integration indeed. But in dynamic case, when, as we see, the crack grows, we have to basically change the partition by integration pieces in order to take into account the change of geometry. For example, at the first of these three pictures, here we have just a solid piece, solid homogeneous piece, and we can take a relatively big polygon without loss of precision, because this is just a piece of homogeneous material. But at the right picture here, we have crack here, we have the irregularity, the geometric irregularity just in this piece. So if we retain big polyhedra like this here in the crack, then we will definitely get very big error. We will definitely get results of computations entirely different from the reality. So we have to remesh. We have to decrease the amount of the size of polyhedra, we have to make many small polyhedra just at the end, at the edge of the crack, in order to take into account the inhomogeneous processes which it introduces. And this is actually a difference, quite a difference, and as it is shown, we can see that especially when small r, as you can see, this fraction which shows the relative speed of the computation tends to grow immediately. So that is to say, as soon as we have the thin crack, it may be somewhat paradoxical, but the thin crack produces much more computation than large crack. Just because the thinner it is, the smaller has to be polyhedra or polygons around it, so the more computation has to be taken to integrate over them all, and this is basically goes to infinity. It was proven that the
actually from like classical point of view, it looks a bit like complex analysis, like remaining problem. So
that's right.
Yeah.
That's right, basically. And so, as we can see, as it is summarized at the lower part of the slide, we have certain issues, troubles associated with finite element methods, such as making a mesh with edges conforming to the crack geometry is time consuming. Then another problem, which is caused not by geometry, but rather by physics, is that different physical forces are best computed over different, usually incompatible meshes. That is to say, when, for example, when you compute the thermal field in some construction, you can build an optimal mesh, optimal with regard to size and amount of polyhedra to which you split it, so that best take into account the heat spread processes. That is, when you have some kind of sources or sinks of heat, you place many small polyhedra, but and somewhere the distance from such specific places, you can use you can use a small amount of rather large polyhedra. But just the same applies when you consider gravitational force, when you consider electromagnetic force, and but in case that a construction such as nuclear reactor is under simultaneous influence of all these forces, so you have, for example, the three forces just listed, so you have three meshes which are generally different. The places where heat, for example, heat mesh is dense, the gravitational mesh may be sparse, and vice versa. If you simply unite them and produce the smallest mesh of all this, this will be very small mesh throughout all the body.
How you choose geometry just empirically try to...
And that's right. And usually people, actually the engineers, just start the magic manipulations. Let's try a bit more dense mesh here, a bit less mesh there, and just until the behavior of the model will be somewhat resembling to the behavior of the real reactor. That is to say, essentially, the solving of the problem is replaced by actually the, as they say, choosing something similar to the known answer. Needless to say, with such a methodology, we cannot resolve really new problem. We have already know the answer. In order to make the mesh such that it produces something similar to this answer, and then we will call it a solution, although actually we would not have any progress if we didn't knew this solution in advance. And actually there is one more problem just to put to this heap. This means that meshes usually don't compose over an assembly structure, especially if constructed by welding or the like. That is, if you build, for example, a plane from wings, fuselage, engines, then it would be very nice to compute the, for example, the stress, the cracks, separately for wings, separately for fuselage, separately for engines, and then expect that the overall fracture parameters of the plane would be some kind of composition, not just a sum, but still some reasonable kind of composition of the results obtained from the pieces, the piecewise computations. But as soon as finite element method is used, this is definitely not the case. For example, when you combine two parts of your construction by welding, then you have to unite polygons or polyhedra, which are at the welding at the edges, which are being welded, in order to have a correct description of physical field propagation at the welding line. And all these issues actively stimulate researchers to find methods for computational fracture mechanics, which are alternative to finite element method. Among these are, for example, so-called strong discontinuity method, extended finite element method, so-called error-adaptive methods, mesh-free methods, methods based on peridynamics, phase field models in brittle fracture, discontinuous Galerkin and polytopic finite element methods, methods for cohesive fracture models, method based on functional voxel geometrical models, movable cellular automatons methods, and actually many others which are not yet so widely known. In the rest of my talk, I will overview some of these methods. For example, extended finite element method suggests to split our mesh to basically two parts, so-called standard part or standard nodes, and so-called enriched nodes with enrichment part. And the basic idea is that with enrichment part, we add certain function depending on the geometry of the here of the crack, in order to take into account the varying geometry of the crack. That is, essentially, it means, as it's shown in the picture, we actually use ordinary finite element methods just in areas outside the cracks, and we introduce special kinds of nodes with special that is special values taken into account the nature of the cracks in order to compute the cracks, and as it was shown by Duflo, we have somewhat more quick and more accurate predictions of crack propagation using such extended approach. But another, and as some researchers think much more perspective approaches are known as so-called mesh-free methods. Here, the idea of the basic idea is to avoid the whole nature, the whole cause. The idea is to eliminate the root cause of the problem, that is the need to build certain specific mesh, that is build a specific polyhedra. It is, instead, as shown in the picture here, instead of building certain specific mesh that takes into account the specific geometry and specific geometry of cracks, etc., we just use the ordinary rectangular or cubical here homogeneous partition of the space, just as ordinary, for example, the very ordinary. This can be considered as somewhat moving back from the Lebesgue integration to Riemann integration. That is to the very and specifically the most simple form of Riemann integration.
If I understood you correctly, it's sensitive to geometry, right? Your result, your model sensitive to geometry of the mesh, or it's not. I understood that it is, right?
That's right. But it is in the algorithms which are developed here, it is suggested to consider the geometry differently. That is, in certain sense, as it is shown in this formula, in certain sense, we put the geometry somewhere inside of well, a physical part or a part that is computed rather than is given from outside. That is to say, I can maybe use the just as I say, just to show what does it mean. In this schema, it may be somewhat cryptic. It may look somewhat cryptic, and I will show on the board what it basically means. I assume that we have some kind of differential equations. We have some kind of physical field, eta of x on some geometric field. Assume that we know the differential equation which describes the behavior of such physical field of the form, for example, d eta equals to 0, where d is the differential operator of some kind. For example, that there can be the Laplacian operator or something much more difficult, non-linear, whatever. This is just the equation. And we have boundary conditions. We have the body omega, and we have the boundary condition that at the boundary of omega, the field is equal to 0. For example, it is some heat field and a vacuum around our body gives such kind of condition. So there is quite difficult geometry of when you use methods like finite element method, you already know the geometry of the body, and you make mesh that reflects this geometry as close as possible. Specific mesh, something like specific Lebesgue measure for Lebesgue integration, in order to reflect this geometry, represent this geometry as accurate as possible, and with all problems with meshes which we are listed above. But you can go ahead just another way. You try to find your field in the form eta equals to alpha multiplied to beta at x, where alpha is a specifically known function which behaves like this. Alpha on the boundary of your body is 0. Alpha on within omega in the inner part of the body is more than 0, and alpha around the omega is less than 0. And so if you choose alpha properly, then you see that the boundary condition is satisfied automatically, no matter which is better. And all you need is to resolve the equation of this kind over the unknown value beta. It is important that the function beta is not subject to any boundary conditions at all. The function beta no longer knows about geometry because all the geometry is taken care of by the function alpha. So, of course, this kind of so it can be considered as a kind of analytical splitting of geometry and physics over different multipliers. The question is to find and as soon as you provide such operation, then you can integrate to find beta just with whatever mesh you like. For example, just with a usual rectangular regular line. It doesn't matter because there is no longer geometry at all. And of course, the question is how to choose alpha the best, so that this equation is not overcomplicated. You can see that if the alpha function is too difficult, then the equation of this kind, when to be resolved over beta, can be so complicated that our supercomputers won't be enough to resolve it. One method, which is basically shown on this diagram, is based on the choice of alpha as a function of Euclidean distance to the boundary. That is no problem. I will show that. Imagine you have your body, you have a point, and you calculate the Euclidean distance, that is the minimal distance between the point x and any point of the boundary. Clearly, and you have this value positive if the point is within the body, and negative if the point is outside of the body, and naturally it will be 0 for all points on the boundary and only for those points. So there is a commercial computer-aided computational fractal mechanic tool called Scan and Solve, which implements this kind of method, this kind of evaluation of the correct propagation and growth processes with this approach and with this kind of function, geometry function, proportional to Euclidean distance, and with the regular rectangular mesh, rectangular partitioning with that is a simplest form of Riemann integration in order to resolve the equation of under beta. And indeed, if you, for example, seen on this picture, if you have some variable geometry such as growing cracks, then you simply add here the time as a parameter, of course. But again, all the difficulties associated with change in geometry can be split just here. Basically, you have omega as a function of time, but as soon as you have reasonably good algorithmic means to compute alpha, so that it remains to be 0 exactly on the boundary, on the varying boundaries of the body and with other behavior as needed, then you can consider the varying geometry such as growing cracks just with basically the same computational means. And this is what actually the authors of such methods are doing, and which we basically generally expect to evolve and to produce more commercial, quite helpful, useful commercial tools in the nearest years. And generally, in line of this approach is a kind of methods which are under development in our Institute for Control Problems. It is known as a functional voxel approach. The idea here is that to augment this kind of it's okay. Now I am just showing to these pictures. I am not going to write down anything else. In this picture, basically shows the main idea that we augment this approach to so-called voxel representation of the geometric model. That is, we derive the function alpha from the not from the analytic representation of the geometry, but from its computer representation of the specific kind, so-called voxel representation. Actually, voxel is an acronym for volumetric pixel. That is, it is basically a three-dimensional raster image, just as ordinary display. This very display is actually actually consists of small pixels in which any image is discretized or rasterized. Just the same in 3 dimension provides so-called voxels, and actually the additive 3-dimensional printing technology can be considered as a material implementation of the voxel structure, since 3-dimensional printer basically prints by very small points of material, different materials in different places, in order to produce however complex geometry. And so voxel approach to geometric modeling allows to derive the geometrical functions such as alpha on that example in quite straight away, and so therefore it allows to derive the physical part, that is better, with rather simplified formula, just as in the example where the propagation of pointed stress is shown, and essentially it allows to perform the crack propagation computations immediately over the geometrical model represented on in a voxel form, and such approach is stable over multiphysics. It doesn't matter how many different physical forces are here. It is stable under multi-material case, since each voxel can be assigned with attributes describing its, for example, the properties of materials from which it builds. It is built no matter which are, and for different voxels, different characteristics can be assigned. And it is stable for to multiple scale, just because the voxel models are proven to compose correctly. That is, basically the geometric and physical functions derived on some parts, voxel models of part of some complex contract.
Excuse me. Is that similar to wavelet transform?
I don't think so, because wavelets are usually produce curved pieces. Here it is shown that even simpler rectangular or cubical pieces are enough. Your analogy can stand in a sense that various processes such as acoustic processes, for example, when written on a wavelet form, are expose themselves much simpler than when written on
Yeah,
the
but the tool is
geometry.
different, but the approach is in the same
Yes,
spirit, no?
it seems the approach is in the same spirit, in the from the point of view that it allows to get simpler representation of physical influence than the original.
To discriminate between scales, right?
That's right.
Okay.
That's right. That's right. Approach to discriminate between scales. Thank you. That is, and just to not to complete, but to continue our overview of alternates to finite element methods, there is an interesting set of methods called period dynamics, which actually its major idea is to switch from differential form of physical description of correct processes and fraction mechanics process to the integral form, meaning that when integral equation, as you see here, the integral equation is growth, and the integral equation's integral form is better in the sense that it doesn't require a priori, as they say, continuity requirements, continuity restrictions. Unlike differential equations, so in order to differentiate, you have to have continuous or even smooth functions. For integral equation, you definitely can have non-smooth or even non-continuous functions, and without such limitations, it is definitely easy to you have at least much more freedom to make mesh even in the traditional mesh method. And so the differential in integral form, you have even with using ordinary finite element methods, you usually have your solutions in less time and rather more stable under various variations. And the basic ideas of period dynamics is the kind of volume forces, volume force model is presented on the picture.
But it's strange that you say it's computationally easier.
Yes.
That's very strange. No, I mean,
Why not?
No, I mean, generally, like integral equations are more difficult than just differential, if you may want to generalize.
The point is that at finite element methods, you have to integrate anyway. You have to integrate it. You have to integrate no matter what you start with, differential or integral form. But when you start with integral form, you have much more freedom in the sense that you can ignore the points of discontinuities, of breaks. I mean the loss of smoothness, etc. Because in integral form there is no operations like dividing two small amounts, one small to another small, and it is computationally more stable and sometimes more fast. And just another model to be considered is the phase field models, which is based on the assumption that as soon as we said, that the break of the solid body solid construction can be thought of as a kind of phase transition, then in the level of physical model, it may be worth to try to describe it as a specific scalar field called phase field, see here, which has a certain addition to Lagrangian, just similar to the one which by which the ordinary phase transitions are described, and get the Euler-Lagrange equations of motion, which takes into account simultaneous dynamic of the deformation U and the phase field C. And essentially, these equations are similar to the classical Ginzburg-Landau model, phase transition model. It is similar to phase transition. And numerical experiments shown in the lower part of the slide show that a kind of stress applied from the left pointly produces various tensions and produces certain non-trivial phase field, and shows where the most probable areas of crack are shown as irregularities in the phase field beginning. So this is also quite promising approach, and this is basically inspired by, as I said, Ginzburg-Landau models or even quantum field theory approaches, where you have the Lagrangian and change, where you start to play with the Lagrangian. You add anything you can imagine into the Lagrangian and see what kind of interesting physical effects you can obtain by that.
I have another question, because this formalism usually is applied to fluids, no? And at some moment you could code the fact that your medium is naturally fluid, and I wonder where this happens in the equations. You understand my question?
Yeah, I see. Actually, what I didn't reproduce here on the slide are the boundary conditions, which are very, very monstrous in this case. And they are specifically these boundary conditions that take into account the fact that you deal with solid rather than fluid. But they would require something like 5 such slides just to list this. So right you are. You seem to see through the root. But I can say that numerically these boundary conditions are not much more difficult than, for example, even usual finite element approach. They are monstrous when written as formula, but they are rather straightforward algorithmically. And this is why this phase field approach has certain potential in computational fractal mechanics. And the last but not the least method to be considered today in my talk is so-called method of movable cellular automatons, whose idea is to represent our solid on a mesoscopic level, but by a set of cellular automatons, which has certain transfer function to transfer influence from one to another to adjacent automatons, as shown in the picture below, and by certain kind of equation that describes the mutual influence of automatons, we eventually, by integrating and averaging, we get the curve which describes the behavior of material under stress. Here the behavior under periodic stress is shown, and the red dots show the experimental results, which, as can be seen with proper usage of various parameters of the automatons, can be reproduced by resolving these equations. Of course, as I said, there are many more methods to be observed, but as I see my time basically is near to expire. So thank you very much for your attention. Questions or comments, please?
I have a question related to your function Einstein beta.
Yes.
There are 2 questions. First, I suppose that there are a kind of undefined problem for function beta near the boundary of the volume, because any function beta is sufficient to satisfy the equation.
That's right.
And second, if the alpha function is Euclidean distance to the boundary of the volume, then generally alpha is not smooth inside the volume. So for example, if we have a rectangular box, then near the center of the box, we have sharp top of the function as a rectangle. But the product of alpha and beta should be smooth. Therefore, beta function should be not smooth to satisfy the expression, and instead the boundary condition we obtain some something like boundary problem near the singular behavior of the beta function in the point where alpha is not smooth.
Right, you are. And actually, both of the concerns that you expressed would be very important if we would try to resolve the equation shown in the circle analytically. But as soon as we resolve them numerically, then first, and we compute both functions numerically, then first we actually don't have, we really don't have any, irregular points, for example, at the center of rectangles, because actually it will be discretized over a rectangular, let me show. I mean that, of course, you have, analytically, you have a function with x, for example, but numerically, you have not a function, but an amount of its values on a discrete finite number of points. And with this finite number of points, you can, as soon as you have this finite number of points, you don't care that at some point its analytical form has an irregularity, equal something. Actually, you have just, or if you would like to go back from from numerical to analytical representation, you are free to smoothen any irregularity just in between the adjacent points.
You can artificially smoothen this.
Yep, exactly. Just because you solve the task numerically up to the given precision. For example, 10 power minus 6, 10 power minus 10 if you wish and you have supercomputer. But in between these distances, you can smoothen whatever you like.
I want you to find problem of the boundary. And what is the meaning of the function beta outside the volume omega?
Nobody cares. As soon as we can compute correct propagation within the body, nobody cares what happens outside.
More questions?
Yes. I mean, your methods are similar to methods which are used in astrophysics, for instance, for the formation of galaxies and things like that. Also in general relativity, and also in climate modelization.
Right.
And so I was wondering if you are in contact with some people using this method, and if you compared your method with others, something like that.
Very good question. Actually, the first mesh-free computational method in history was invented about 1980s for the computational astrophysics. By the computational astrophysics team, it is called SPH, spread particle hydrodynamics, and indeed it was quite inspiring for the solid body physicists to use to get rid of the difficult dominations associated with meshes, with finite element meshes. And so indeed, you are quite right that computational astrophysics specifically, although it may be not evident, but indeed computational astrophysics specifically was of large help for development alternatives to finite element and such mechanics.
And do you follow the present state of the art in the simulations?
More or less, that is to say, it is quite difficult for a single man to follow everything, but yes, generally we try to stay on top and incorporate recent ideas.
And maybe I come back to wavelets because I think if you make a wavelet transform. Sorry?
I did not understand really.
Wavelet transform.
Yeah, I heard about that, but could you just elaborate and explain the analogy, which I didn't understand actually?
Well, my question was about the similarity between such methods and methods using wavelet transform. In fact, wavelet transform is something, is some kind of way of coding image in 2 dimensions or volume in 2 dimensions.
It's kind of computational Fourier transform.
Yes, but it's different than Fourier because it's more efficient in some sense, and it shares with Fourier the characteristic that if you make a wavelet transform, then from the Fourier transform you can reconstruct the image or the volume, and this is very efficient in saving information. This is why this is at the basis of the JPEG compression formalism in image treatment. So I think the main advantage compared to other methods is that it allows image or volume or reconstruction with very economy of computer memory.
Yeah, that's right.
But it's not easy for dynamics because usually it's not non-linear. So, but at some moment I tried to do that in astrophysics without success. So I was curious to ask if somebody is doing that.
Yeah. And in solids we actually gained some progress, and we expect to gain more. Here in I think that for solids this would work somewhat, as we say, more, well, as we would say, more intense or something. Is compared to astrophysics.
I have kind of philosophical question. The example you've given look like very kind of concrete example, right? You have a really, I don't know, plain, a real material thing, and then you use mathematical tools, and in a sense, in some cases, in kind of naive way, right? So you, I don't know, basically the mesh, you can triangulate your body or something. So that kind of, at the same time, actually, it appears that the same mathematical apparatus also applied in kind of more fundamental physics in astrophysics, and also no, we didn't talk about that today, but we discussed the earlier, like category theory. So,
that's right.
So apparently we also use very kind of abstract mathematical concepts, right?
Definitely.
And actually we didn't develop this polytope. That I know also from
from topology. That's right.
Yeah, complex geometry.
Entirely.
So the question is how it works. Whether, say, there are kind of more concrete examples and then more abstract. Is there a kind of continuum spectrum of such application, or there is perhaps some boundary between cases when you use it very concretely or abstractly? How you think
on my opinion, I see the question is indeed very philosophical. On my opinion, that actually stems from the fact that actually we are capable to ask very small range of different questions. At first, the very first my slide, the questions of the kind, the questions that enlisted, you can just replace specific terms such as crack size, initial size, and obtain almost every question which is asked on different fields of physics, engineering, computer science, techniques, etc. Actually, we are interested in a very narrow area of events, of things around us. We look around, we look around widely, but we see very few things, and we are capable to ask very few questions, very few conceptually different questions about very few conceptually different things. And it isn't surprising that we constantly gain very few conceptually different answers in very few conceptually different terms. This is basically, and this is not, I'm not saying that the human mind is weak, is defected, or something. This is just, at least in our relations with physical world, we have very limited amount of sensors and very limited amount of actuators. And the same in terms of control theory, we are very robust control system, and so we keep asking quite the same questions and keep receiving quite the same stimulus, and so we keep sticking to quite the same concept.
But actually, a similar question here in the beginning, you mentioned that this science, right, needs to be, as you put it, multi-physical.
Yeah.
Yeah. But I just wonder, and now we see that still you use, as you just stressed, concepts which you share actually with also different parts of physics. But question is how you constitute this multi-physical, whether you think about that as, how to say, kind of independent, self-standing discipline. Put it that way. How do you think about relations, say, of this particular, let's say, model, and all these ranges of physics which are involved?
In terms of mathematical physics, you just keep enriching this operator D by, as I said, contributions from different physical influences. For example, if this is kind of Newtonian equation, just as we see, for example, you have the deformations U, actually this a field of deformation in elastic bodies, U, and you have Newtonian equation of the kind of U two dots by time, double variable by time is equals to so-called elasticity forces, which is basically given by the Laplacian with some coefficient, plus F, where F is the external forces, which is in turn additively, which is a sum of gravitational force, such as rho G, plus electromagnetic fields, such as the density of charge multiplied by tension of electromagnetic field, plus etc. So this stands for F. And essentially, that is it is, well, at least in Lagrangian physics, it is not proven, but well explained. It is ground that the various different physical forces act additively, and sometimes certain kind of for example, if we will operate in astrophysical scale and use quantum gravity or something, we will get some kind of more difficult composition, but yet it is going to be some kind of composition between forces, and it can be obtained via Euler-Lagrange method from the appropriate Lagrangian. And by the way, the interesting thing is actually that the form of this equation over deformation field is actually the same as the form of electromagnetic field dynamics, where instead of deformation you will use the vector potential. Only you will get it. This one you get in 3 dimensions, and electromagnetic field you get in 4 dimensions, in the 4-dimensional space-time continuum. That is to say, this all shows that again, as soon as we are interested in very few different things, then we get very few different schemas to describe it mathematically.
More questions? Huh? Okay, thank you.
Thank you so much.
C'est dans mon ordinateur. Tu peux regarder, tu sais peut-être comment. C'est quelque chose un peu plus délicat que ce mot de passe.
Un identificateur et mot de passe.
Mais si tu peux le lire sur mon ordi, c'est le classement.
Non, ah, j'ai compris.
C'est compris, je vois pas. Je sais pas, c'est le mec qui m'a fait. Je crois que c'est plus que seulement mot de passe. C'est réseau interne, tu vois, quelque chose de ce genre.
Je comprends.
Ну, так, например, это получалось. То есть я понимаю, что такое, в принципе, я понимаю риски, которые это такие. Нет, на самом деле это вполне возможно такие, но здесь опять же нас интересует конечная точность. То есть получив как точность, которую мы хотим, мы дальше уже не все решить. Ну, вроде бы да. Вроде бы да. Ну, там есть определенные люди, которые задевают часть. Ну, нет, это не называется. Возможно, как уровень. Это точно так и есть, потому что, собственно, современные вот эти конструкторы, они как раз собираются до уровня сложности, как раз как есть канализм. А дальше просто выражают, что вот я выбрал вот для данного доклада как бы конкретный разрез, да, это проблематика разрушения образования трещин. Но, конечно, это все идет в общую канву, просто в этой части своей, ну, скажем, специфические постановки, специфические результаты, которые Андрей Константинович говорит, что делать усилия, это да? Вот, само собой, приложение к экологии, например, психологии и так дальше, мы вполне спокойно могли получить такого же рода картины, тоже с другими немножко. Ну, собственно, как бы я ответил на вопрос Андрея. Мы задаем очень мало разных вопросов, очень мало разных. Нет ничего свидетельного, что происходит, даже очень разных относительно к заготовлению. Если безусловно так есть, все это движется, кажется ровно в этом направлении, то есть том, что исследовать поведение зрителя невозможно, не приняв во внимание роль те самые системные факторы, которые нужны для управления государством.
Что происходит современном, в принципе, происходит разрушение, потом вы узнаете, что есть.
Вот это как раз и есть неприятность концептуального подхода, что его надо понимать, как-то маркировать, как вот это вот механика метод принципа элементов не приспособлена для такого рода операций. Поэтому он получает, по сути, вы всегда какая-то шаги как-то перестраивать то есть это все долго, это чревато накоплением ошибок, мы контролируем, и в итоге получается, конечно, что-то те же самые конструктора автомобилей, может не верят тому, что надо посчитать, тому, что в частности, не видят они похожего на реальные выгоды.
Раньше граничного поезда свободной границы, чуть больше
Конечно, конечно, все. Поэтому в этом смысле беседочные методы эффективны. Спасибо.
I have to find where my paper is in order to open it. Do you know the password to the Wi-Fi here?
Here?
Yeah.
No, I don't know. There is Wi-Fi now?
Yeah, there's Wi-Fi, but we need a password which I don't know.
нужно вам objective reality that considers chaotic information cosmology. This is some theory that puts the very good prediction for cosmological background, entropy, and so on. But this model contains such things like other universes. And it couldn't work without other universes. What do you think about other universes?
I think well, I give an analysis. Yes, I give an analysis. Suppose that you're in order you have a real integral diffusion, and you use the method of radical, which involves complex numbers. You don't have to you don't have to believe that complex numbers have anything to do with real measurements, like real numbers, in order to use complex numbers. What's going on? Because when you move to complex field, you have more formal possibilities, and you can use this extra formal root in order to understand the formal properties of subdomains. And that's the same thing going on in current. Of course, all the universes are there only as formal entities.
I can ask if there exists some observers. What they think about that?
I don't think that they necessarily cannot exist in reality.
What kind of reality?
Yeah, but it's just formal. It's just formal. You can try how you just talk about geometry method really is a formal property. Anything takes part in theory and as actor in a formal elements they are irrelevant. So that's why we when it comes to any physical theory, you can put up just how much gem as you want. You can suppose that you have a length dimension of space. You can suppose whatever. It's not corresponding to anything real. The only thing they have to do is to help clarify formal properties of your experience. And that's all that you need. Many physicists can play with fantasies of universes not fantasy. Yeah, I know. Good prediction. Of course, a good prediction. Of course, it's not a good prediction.
I reckon the case that if it's a kind of myth,
Yeah.
they know, the theory can do good prediction.
But my point is that for the I also mentioned this in my talk. If theory can make absolute precise predictions without deviation. In an ontological strong sense. I just mentioned in my talk. If you get all this, it works marvelously well. It works marvelously well. You know, but from our perspective, it's a wrong model of reality. It's a wrong model of reality, but it works all the same. And the thing is that the fact that the theory works only indicates that it's formally correct. It's formally correct. And there is a big difference between being formally correct and materially correct. Materially correct means corresponding to an ontological entity, a sort of referential.
Сейчас, давай тогда. Сейчас. Oui, j'ai mis mon mot de passe. C'est mon mot de passe cher. CSER.
C'est ça, alors, ouais,
Что-то сейчас
d'accord.
прям надо распечатать, да?
А ты вообще как долго в Москве?
Слушай, я нет, еще завтра, послезавтра.
Ну, так можешь с вами договориться, договориться.
Да? Ну давай, ты еще.
Может быть, я даже сегодня ближе к вечеру подъеду. То есть тут будет как по расписанию или как?
Ну да. Ну и, наверное, вечером мы тут пойдем там что-то ужинать.
А, ну так слушай, может быть, как...
Да, ну давай,
Тогда
тогда
это...
распечатаем.
Да.
Там ближе к концу.
Да. То есть вот я, наверное, где-то в районе круглого стола. Может быть, я и подъеду просто.
Да, я тут расписание не дам.
Самое удобное, потому что я сейчас просто веду всякие дела,
Ну,
а
понятно.
к концу я бы даже в этом столе бы переключил.
Ну,
давай.
André, tu veux que je te montre? Tu vas dans Applications. Dans Applications, il faut aller dans Utilitaire, je pense. C'est où ça? Utilities. Keychain Access.
Et voilà.
Hein, il veut plus?
C'est parce que c'est déjà ouvert?
Oui, peut-être.
Oui, d'accord.
Ah. No, sorry. Ah, Keychain Access.
Yes. Just Mark needs you want. Okay. Okay. You can give us some way.
Donc tu vas dans Keychain Access. Tu as la liste, quoi? Tu as la liste tu vois, de tous tes logins, de tous tes mots de passe. Alors tu regardes là-dedans et tu vois, je l'ai vu, mais...
Attends, mais c'est bien, je trouvais.
Ouais, attention, ouais.
Bon, d'accord.
Non, mais regarde, tu vois, IPH, tu cliques là-dessus, voilà. Et si tu veux connaître ton password, tu fais Show Password et il te demande ton autre mot de passe pour montrer. Ok?
D'accord. Bon. Ok.
J'essaye.
Ah, mais il dit que c'est que pour ces ordinateurs, tu vois, c'est peut-être le numéro physique de machine qui est dedans aussi.
On va voir.
Ok. Sauf que c'est sur YouTube, mais password, c'est pas mal. Parce que c'est tout ça enregistré à YouTube.
Non.
Mais je peux éditer après. Ok. Bon.
Je crois que ça marche.
Ça marche?
Je crois.
Super. Сейчас он вернется, все, мы начинаем. Okay. Let's begin. Сергей, we'll
Ready?
come back to...
Are we ready?
По-моему, да. It's 11.
It says 11:15 in this anyway.
Okay.
We can start anytime you want.
Okay, let's wait 11:15 right here. Sorry. Okay. Yeah, I still have some minutes.
Yes.
Okay, well, so we coming back from applied mathematics to philosophy, and we are pleased to present here Jairo da Silva from São Paulo, who will talk on applicability of mathematics in physics.
Yes, thank you very much, and thank you for the invitation, Andre, and also Irina. She's not here, but I'd like to thank her for her kind invitation. Okay, Many of the people who spoke before me mentioned, this issue of the philosophical issue of the applicability of mathematics in physics. I want to, to approach this head on because I'm not taking this as a only a side remark, but it's something essential to my consideration. So what I'm going to do is I wrote a sort of paper for this meeting. So what I'm going to do is just go through what I wrote, and you read it with me, and we make comments. I may jump a bit when I find that they are not quite essential for the discussion. Okay, and you have to excuse my style because it was written in a hurry, and I didn't have time to revise or correct it. So there we go then. Then Eugene Wigner closes his famous paper, the one we know about, with this quotation. The miracle of, it's funny that how many times the word miracle appears in that paper. It's really annoying. The miracle of the appropriateness of the language mathematics for the formulation of the laws of physics is a wonderful gift which we neither understand nor deserve. We should be grateful for it and hope that will remain valid in future research and that it will extend for better or for worse to our pleasure, even though perhaps also to our bafflement to wide branches of learning. Okay, I believe that Wigner's bafflement vis-à-vis the unreasonable vis-à-vis the usefulness and the miraculous adequacy of mathematics, its languages and concepts for the formulation of the concepts and laws of physics, and as Mark Steiner, another philosopher who, presents even more dramatic views on this issue, later emphasizes sometimes for the discovery of these laws as well. Steiner is particularly concerned with the heuristic role of mathematics in physics. Betrays hidden presuppositions, which by remaining hidden block the way to the adequate understanding of what should be straightforward scientific methodology. I find one of the jobs of the philosopher is to uncover hidden presuppositions, because the hidden presuppositions can be very nasty. People are not aware of them. Okay? And then they take hidden presuppositions as established truth. And sometimes they are not. They're just presuppositions that you have to bring out into the light in order to examine them. That's what I'm planning to do here. My goal here is to bring to light these presuppositions and offer alternative views, particularly on the nature of mathematics and physics, which I believe go a long way into dispelling the fog of mystery that surrounds the efficacy of mathematics as an instrument of scientific inquiry. Either mathematics and physics are what Wigner thinks they are, and the applicability of mathematics in science constitutes indeed a miracle, or miracles do not happen, and Wigner's views on the nature of mathematics and physics are incorrect. At the heart of Wigner's bafflement... Yes, if you feel...
Just from the same viewpoint, because my reading of this way, I also was kind of, outraged and right?
Yeah.
We share emotion. But my understanding is that he kind of just doesn't want to discuss it. He just says it's a miracle, that's it.
It's a miracle that hits you what's up.
But when you say he's incorrect,
he's incorrect because his presuppositions are not correct. That's what I want to analyze, the presuppositions.
Okay, you make it explicit.
Yes, I make it explicit. At the heart of Wigner's bafflement lies the presupposition that whereas mathematics is essentially concerned with its own concepts, divided for the most part without any particular regard for empirical reality, physics is concerned with the world, the physical world, conceived as an independent realm of being existing in itself and completely determined once and for all. Wigner carves an abyss between mathematics and physics, and it would be surprising indeed if he did not fall into it. There is indeed absolutely no reason, a priori, why man-created mathematics should have any relevance for the description of man-independent empirical reality, to the point of being essential for even the formulation of its laws. It is unquestionable that mathematics is a creation of man. Although some mathematics is invented for the purpose of coping with some aspects of human experience, I jumped to this here, or the convenience of science, mathematical concepts in general are free creations which answer for the most part to mathematical conveniences only. This is a fact. Most of mathematics is created for mathematical purposes. That's it. Physics, on the other hand, is concerned with an external world. And if the applicability of mathematics in physics is to cease to be a mystery, physical reality cannot be what Wigner thinks it is, an independent reality existing in itself, but miraculously willing to open its secrets to mathematical concepts, to the point of demanding mathematics for its laws to be expressed. If mathematics is part of the very fabric of nature, but happens to agree with man-made mathematics, which is seldom created by observing nature, then there must be a link of some sort, causal or otherwise, for example, pre-established harmony between human mathematics, a cultural product, and the mathematics of nature. Some people have advanced a naturalistic explanation for this miraculous appropriateness of human mathematics for the description of nature, along the following lines. These people say, since man was naturally selected to survive in this world, it's not at all surprising that man was also naturally selected to create instruments for understanding how this world functions. This is a common strategy to try to use natural evolution to account for certain facts. The problem with this line of reason, there is a grammatical mistake here. The problem with this line of reasoning is that among the strategies selected for the survival of men and to the age of reproduction, there is no among here, that the strategies do not include the understanding of, say, the laws of quantum mechanics. On the contrary, the concepts necessary for the adequate explanation of quantum phenomena conflicts with those developed for surviving the world. For instance, the concept of a trajectory of a body. And the determinacy and unicity of trajectories given a dynamic situation. Of course, we developed the notion of these classical notions. We could explain the development of classical notions as a consequence of our adaptation to the environment. But, the adaptation to the environment does not require any understanding of quantum phenomena, right? Absolutely none at all. My approach here is a different one. Unlike Wigner and others who never question their realistic empiricist presuppositions, I tell where I come from. I take a transcendental idealist perspective of the type proposed by Edmund Husserl, the patron of this room, by the way, particularly in his masterpiece, The Crisis of European Science and Transcendental Phenomenology, where the intentional genesis of the concept of empirical nature proper to modern science, as created by Galileo and others, from the 16th century on, is scrutinized. I claim, in agreement with Husserl, that the concept of nature prevalent in the modern mathematical science of nature is an intentional construct, elaborated for specific methodological purposes. The scientific concept of empirical nature of modern science is an abstract and idealized... What?
Just a little bit slower.
Oh, because I thought you were reading. Okay, I go slower. The scientific concept, because I tend to read fast.
No, we have time.
Okay. The scientific concept of empirical nature of modern science is an abstract and idealized representation of some aspects of our immediate perceptual experience of nature, is specifically designed for mathematical intervention. So my point is that the nature which physical sciences study is not something independent of intentional construction. The concept of nature is an intentional construct, and constructed precisely to allow mathematics to intervene substantially in our investigation of this object, right? Unlike Wigner, I do not presuppose that science provides a direct, non-intermediate description of nature, a view whose corollary, and with it the mystery of the unreasonable effectiveness of mathematics in science, is that the mathematics that science finds essential for the description of nature must ipso facto be an essential aspect of nature. The fact that some mathematics is essential to formulate the laws of nature does not imply that mathematics is by necessity part of the fabric of nature. Okay? Something intrinsic to it, to nature. Now I say, I see, it's not moving fast enough. Why? Yeah. I see three layers. Now it is. See, let's go back. I see three layers of reality, where Wigner apparently sees only one. There is, I believe, nature out there, somehow causally responsible for a second layer of reality, perceptual nature, which is either directly grasped through the perceptual system or somehow inferred from perceptual data with the help of our theories of nature. The part of perceptual nature which is not directly perceived is nonetheless supposed to be in principle at least accessible to immediate experience. And finally, the mathematical construct by which science represents some aspect of perceptual nature. I will call these levels respectively nature with a capital N. Nature is out there, okay? Nature is nature. And science is not concerned with nature. Science is concerned with a representation of that obtained through our perceptual systems. But our perceptual systems are not windows to nature. They are active. They are active into constructing a working model of nature. Okay? A perceptual nature, and then I call nature, perceptual nature, and physical nature. Physical nature is the object of physics.
But do you consider perception itself as a part of nature or not?
Of course, yes. Of course, it must be. By which understanding concept of nature of modern physics. Perception cannot reach physical nature. Reason only, and with it mathematics has access to it. See, there is a common mistake that we can perceive nature as nature is representing physical science. We cannot. And we cannot for the simple reason that the physical reality of physical science is a mathematical construct, and we do not have a perceptual approach to mathematical entities. We have only rational approach to mathematical entities. We cannot perceive a mathematical object with our senses. This is true.
Yeah, that's right. But when you say perception cannot reach physical nature, that really depends what you mean by reach. Because if you agree...
perceptually.
But it is a part of nature. It just...
Yeah, well, in this sense, it's part of nature, but I'm not talking about this nature. I'm talking about a nature that is supposedly beyond perception, something that's out there. Anyway, of course, there are details here, but I'm giving the general picture. Perception cannot reach physical nature, reason only, and with it mathematics has access to it. But we must refrain from committing the Platonic mistake or the Platonist mistake of reversing ontological priorities by enthroning physical nature as a true nature, identifying it with nature herself, and perceptual nature as only an imperfect glimpse of a reality that is forever out of an adequate grasp. The primary object of physics is physical nature, and through it, perceptual nature, which is how nature presents herself to us. Mathematics is the language of physics, but the distance, the intentional distance, I might say, between physical nature and the nature herself blocks the way to the migration of mathematics from theory to reality. I emphasized before that physical nature is an abstract and idealized version of some aspects of perceptual nature, not all, some. And I will be more explicit about this below. But it is not difficult to guess what these aspects are. Perceptual nature presents herself as a combination of content and form. This is a classical Aristotelian distinction, right? Although, contrary to logical empiricist tenets, I do not believe that elementary sense impressions of the sort, this red patch here now, are the sole immediate giving of perceptual experience. I assume that the hyletic material content of experience can be ultimately reduced to that. Perceptual experience is always constituted by matter, ultimately reduced to sense data, and form, and it is not clear to what extent the form is discernible in perceptual experiences and intrinsic to nature, or contrarily, imposed on sense data by intentional operations of perceptual systems. But only the forms perceived in experience can expect to find a place in physical nature. See, here I pointed to something. Perceptual systems are intentional systems. This means that they act in order to make sense of perception. Perception is not something that a direct link between consciousness and reality, which is supposed to exist independently of consciousness. Perception is an intricate system which has an intentional role of making sense. When I say intentional, I say basically acting to make sense. Our intentional systems act making sense of sense data. So it has an intentional function. By doing that, we are already imprinting on nature certain human features. Necessarily, we are not an open window to reality. We are active subjects. And this is important. We are not passive receivers. We are active subjects. And this is important. I emphasized before that physical nature is I read that already, right? Yes. Yes, where am I? In this sense, physical nature is a formal, abstract reduction of perceptual nature. In its formal aspects, perceptual nature is already, to some extent, mathematical, proto-mathematical, but by idealization, that is, by an intentional process of exactification, the forms perceived in experience become fully mathematical. This indeed, these idealized forms constitute the original community of denizens of physical nature, the material content of which, being either dismissed as essentially subjective or preserved by being given objective mathematical, that is, formal representatives. This will become clear in the sequence. But, and this is very important, physical nature can be arbitrarily enriched by forms that are not the idealized versions of forms immediately given perception, introduced therein in order to more adequately handle mathematically those which are. See, my point is, once certain forms that are perceived are idealized and made properly mathematical objects, then I somehow reduce the perceptual nature to a mathematical substrate. Now, as a mathematical substrate, it can be enlarged mathematically to the point I feel adequate, right? It's like for instance, if I have in mathematics, if I have a domain of entities like the real numbers, for instance, I wanted to develop the theory of real numbers, I can very well enlarge this domain by adding, for instance, complex numbers, enlarge everything to a much larger theory, of which the theory I was originally interested on is a part. And then I can use logical ways of moving from a larger to a domain to a subdomain, and derive mathematical properties of the subdomain from my knowledge of the mathematical structure of the larger domain. Like, for instance, I can use complex analysis to prove things in real analysis, right? The same thing happens in empirical science. The same thing happens in empirical science. I can compute a real integral by residual method.
I think, for example, if you want to use complex geometry in real geometry, there is no much passage.
Yeah, well, but it is not always the case. But it happens often that is the case, right? It happens often that it is the case. That you, for instance, in arithmetic, we use a very heavy analytic instrument to understand the numbers, right? And this is a classical example how we can move from a narrow context to a larger context, which is mathematically much richer in order to derive conclusions about the narrow domain. This happens in physics too. And it can happen in physics because my first move was to make perceptual experience or certain aspects of it, which I isolated and idealized. I can make then certain aspects of perceptual nature into a mathematical domain, right? Now, these forms can correspond to forms in principle perceived in experience, being then idealized versions of those, or be only purely mathematical accretions to physical nature required on grounds of theoretical reason. Mathematically enriched enlargements of what we could call the primordial physical nature. I call the primordial physical nature that mathematical reduct of some things, of forms which actually perceived. That is, the physical nature that corresponds to actual perceptual experiences provide in general more adequate context for higher level mathematization. Mathematical manipulations in the theory, referring either to primordial physical nature or its formal enlargements, may point out to facts that are in principle perceived, but only indirectly and exclusively with respect to their form. Thus, mathematics plays a risky role in science. The particular material content of mathematically predicted phenomena, however, may not be a priori determinable if involving mathematical terms which do not have a predetermined interpretations, or univocally determined even in cases where there is a semantic context available for interpreting all the mathematical terms involved. I try to explain this. Once I enlarged my primordial physical nature mathematically, I can use this extra mathematical truth in order to derive consequences about the perceptual nature. But not materially, only formally. What I can find out is how certain forms, I can only predict certain possible forms of experience, not their material content. That's why I can use sometimes mathematical manipulations that point to certain regularities that can in principle be perceived. But mathematics doesn't tell you how this is going to be perceived. What is the material content of it? Only certain form of regularity. And then I can somehow try to guess what the material content is going to be. I will give examples later. The particular material content of mathematically predicted phenomena, however, may not be a priori determined if involving mathematical terms which do not have predetermined interpretations. Okay, I've already read that. Finding a context of interpretation in perceptual nature or a particular interpretation of a pre-given semantic context which conveniently idealizes makes a determinate mathematical prediction true, counts as an empirical verification of this prediction. But most importantly, this is not a test for mathematics and depends heavily on the science's ingenuity. The possibility of arbitrarily extending physical reality into more and more mathematically sophisticated domains accounts for the extraordinary power of mathematics in our theories of nature, both descriptively and heuristically. But we must keep constantly in mind that it's not nature herself standing out there, or even perceptual nature that mathematized physics is describing, but a surrogate of the latter that only indirectly and only by retracing backwards the steps of the intentional constitution of physical nature refers to the former. This introduction presents in a rough sketch the main points of the alternative view that I want to offer in contraposition to Wigner's naive approach, which I believe is the sole reason why the qualification reasonable is connected with the effectiveness of mathematics in empirical science. Now, what I'm going to do now is that if you remember Wigner's paper, he presents the characterization of mathematics, one of physics, and then shows how the applicability of the former into the later is a mystery, right? So, in order to destroy this order of mystery, I'm going to recharacterize mathematics and physics in order to show that the applicability of one into the other is not a mystery, right? So, what is mathematics? Mathematics, for Wigner, mathematics is a science of concepts, which are either divided for describing entities of experience, as for instance in geometry, or freely invented, in which case they obey only the rules that were created for operating with them. The latter are more common in advanced areas of mathematics, which play such an important role in physics. This characterization can, I believe, be accepted without much reservation. Now, the role concepts play in mathematics, however, deserve closer scrutiny. Concepts are tools of the understanding for categorizing objects, intuitions, perceptual data, and similar individuals, in order for them to be taught. According to Kant, we think through concepts. So concepts must be able to circumscribe well-determined realms of objects, of whatever count as given to understanding. Sometimes objects are given independently of concepts, which are abstracted from them and characterized through common notes. But sometimes objects are given through concepts, which are both means of donation of and tools for thinking about objects. In mathematics, both cases occur. Theorizing about a determinate domain of objects requires a language in which objects and concepts are denoted by respectively nominal and conceptual terms. Explicitly characterization of concepts also require convenient linguistic and conceptual apparatuses. A conceptual characterization is adequate if it succeeds in singling out descriptively the domain or extension of the concept. Either the objects from which the concept is abstract or those the concept is proposed to characterize. The explicit characterization of concepts should then, at least ideally, univocally determine the domain of the concept. We are going to see this is not possible. The categories of mathematics are essentially those of object and relation. Mathematical descriptions are essentially descriptions of objects in relation, linguistically expressed respectively by nominal and relational terms. Mathematical descriptions can only hope to fix a domain of reference by establishing relations among objects of the domain and relations defined therein, in particular by means of properties, a particular type of relation. A typical characterization of a mathematical concept is that of finite cardinal number by the second-order Dedekind-Peano system of axioms. The problem is that no linguistic characterization of any concept whatsoever, particularly in mathematics, is ever adequate. Domains of objects can only be uniquely determined intuitively, that is, by the immediate presentation of their objects in person, so to speak. For example, in perception of some form of intuition.
I just trying to understand a typical characterization of mathematical concept is that finite cardinal number. It's like an example? Or?
Yeah, an example. It's an example.
Okay.
Yeah. It's a typical in the sense of, this is a good example. Yeah. The problem is that no linguistic characterization of any concept whatsoever, particularly mathematics, is ever adequate. Domains of objects can only be determined intuitively. Of course, the intuitive realm of numbers is a model of the Dedekind-Peano system, but it's not the only one. Even though second-order arithmetic is categorical, we can always artificially concoct domains of number-like entities isomorphic to the realm of numbers proper that also satisfy the axioms. In order to circumscribe the axiomatic characterization of the concept of number to its intended interpretation, we must resort to the original donation of this domain, numerical intuition. By purely descriptive means, in language only, we cannot ever adequately characterize concepts. You summarize this. Every time you want to characterize a domain of objects by a theory, you fail to do it. Why? Because no matter how well designed your theory is, it will admit non-intended models. Always. Always. And then we can never characterize, oh, this is the domain I want by a theory. At best, you characterize something that this domain has in common with all the isomorphic domains that can also be models of the theory. Of course, there could be models that are not even isomorphic to the one you want. But in the best possible cases, when you get a categorical theory, even in the best possible case, you are not grasping what you meant to grasp.
Okay, but then, okay, I agree with that absolutely, but then actually it depends how you really think about object. Or you may think kind of negatively, just saying, okay, there are all description and...
No, of course. But
or you may somehow make it constructive.
Yeah, well, what I mean is that objects in the sense of something that it has are individuals, okay? Individuals. And they are individual entities. And they are materially complete. So in this sense, in the classical sense of object, of course, I can devise a sense of object which is, I would call it formal object. And I can say, well, I can characterize a formal object, okay? But I'm not talking about this object. Okay, this is relevant when considering concepts that are not abstracted from intuitively given objects, but freely invented. As we saw, in this case, the concept itself is the means of donation of the objects that fall under it. Let's consider Dedekind-Peano axiomatic system from this perspective. Numbers are no longer simply described by the axioms. They are instead defined by them. The numerical domain is now, by definition, the domain of entities that satisfy the axioms. But as we've just seen, the axiomatic characterization is unable to single out a domain of well-determined objects, the numbers, and not mere number-like entities. The conclusion is that freely invented concepts cannot ever be donators of objects. If by objects we mean well-determined individuals, they can at best single out object forms, or to use Husserlian terminology, formal objects, determined as the form, but indeterminate as to material content. But there is something that the Dedekind-Peano system succeeds in characterizing. Namely, the way in which the objects in any of its interpretations relate to each other. I will call the properties of a structured domain of objects, that is, a system formed by a collection of objects and relations defined therein, which only involve these objects with respect to these relations, the structural properties of the domain. Structural properties are expressible in any language that can be interpreted in the system, and only in them. I will call these descriptions structural descriptions. They can be classified with respect to the language in which they are given, first order, second order, etc. Structural properties are formal in the sense that different structured systems can have the same structural properties. See, formal properties can be the same in different structured systems, not only similar, but the same. The characters of this formal, the characters of abstract entities, that they can appear as the same in different material contexts. Okay? The axioms of Dedekind-Peano express formal structural properties that are shared by an entire family of isomorphic structured systems, and these only. I will call such a system a structure. Then, what is a structure? A structure is a family of isomorphic structured systems. Okay? A structure is then a class of isomorphisms, or, in a more philosophical perspective, an abstract entity, a form, which is indifferently embodied in any member of the class, and which can be intuited provided the necessary intuitive act is performed, abstraction in this case. Abstraction is an intuitive act by which I can move from a structured system to its formal structure. Or emptily meant by a categorical system of axioms. Then there's two ways by which I can be given a structure. By a categorical system of axioms, which are rare, or by abstracting the structure from a given structured system. What to abstract means? To abstract means to see the same in a family of isomorphic structures. The Dedekind piano axiom system in particular characterizes the numerical omega structure determined by the successor relation, which can be embodied in objectual domains that have nothing to do with numbers or the succession relation proper. Conceptual descriptions in mathematics, but not only mathematics, boil down to structural descriptions of the extension of the concepts described. We often use concepts assisted by intuition, which fix intended domains of application. The fact, however, remains that the descriptions of concepts, no matter how accurately carried out, are only formal structural descriptions. They hold in the domains of the concepts envisaged, but also in all domains isomorphic to them. This alone accounts for the range of applicability of mathematical concepts, which often extrapolate the context in which they are created. See, here we have a reason why mathematics can be applied to other domains, to domains different from those for which they were created, because mathematics deals only with formal structural description. Since these are abstract aspects of that domain, and since abstract aspects of a domain can be the same in different domains, I can deal with different domains with the same instrument that I use for dealing with that specific domain. Everything has to do with the property of a formal abstract entity of different instantiations. Okay? In short, to the extent that mathematics involves language and the linguistic characterization of its concepts, it must be content with expressing only structural properties of conceptually circumscribed domains of objects. It is then more appropriate to characterize mathematics as the science of structures or families of structures which are either abstracted from intuitively given structured domains or freely invented. So, what's my characterization of mathematics? Mathematics is our science of structures, either perceived somehow in given domains of entities or just freely invented. The interesting thing is that once I moved to this purely abstract level, I can make it as forms, so to speak, talk to each other. I can develop logical connections between forms. Forms that are actually instantiated and forms that are only invented for the purpose of, theoretical reasons. Then I can make forms somehow dialogue with each other. I can develop a general theory of forms which involve not only forms that in some sense exist, but forms which do not exist and were just freely invented. Now comes to physics. Wegener has a very funny characterization of physics. He says, the physicist is interested in discovering the laws of inanimate nature. The physicist is interested in discovering the laws of inanimate nature. Can you see how many presuppositions are hidden here? Okay, this pretty much characterizes physics for him. Inanimate nature is submitted to laws. The role of physics is to discover these laws. This simple, apparently undisputable claim harbors presuppositions that are so ingrained in our way of thinking that are not even noted. It is my belief that only by uncovering the many layers of hidden presuppositions beneath our conception of nature that we can hope to dispel the mystery that surrounds the effectiveness of mathematics and physics. Here are some. The realist presupposition that nature is a given, which perception and understanding simply stumble upon. Nature is given, our perceptual system, our rational systems just find us and try to make sense of it. The presupposition that nature is submitted to laws. It's funny that we put it this way. It is a presupposition. It follows from 1 and 2 that the laws of nature are intrinsic to nature and have nothing to do with our particular way of experiencing nature and categorizing our experiences of nature.
Nature is then critically taken as a closed domain of being, completely determined in itself and submit to laws, the task of the natural scientist being that of discovering the laws of nature. Let's consider this first presupposition. Nature is a given which we apprehend in perception. We perceive nature herself. This is the presupposition. According to this presupposition, perception has no part in shaping nature as we perceive it. Evidence, however, indicated that perceptual systems play an active role in perception. Indeed, the first task of the sense is to filter. Our eyes are sensitive to only a small fraction of the electromagnetic spectrum. Our ears can perceive only a reduced range of frequencies, and so on. But more importantly, the perceptual systems operate in association with pre-categorical, built-in intentional systems, whose task is to make sense of sensory impressions. Instead of an incoherent mass of data coming from the senses, we perceive objects, objects in relation, patterns of objects, phenomena, process. Perception is an intentional act, and nature as perceived, that is, perceptual nature, seems to bear to a considerable extent our imprint. If this is true, the immediate object of physics is not nature out there, simply given to us, what I call the nature with a capital N, but perceptual nature, intentionally elaborated by us, or still something erected on the basis of perceptual nature. This is important. This is important. Our only approach to what nature is through the senses and reason, right? And primordially, nature is what is given to us through our senses.
Well, I agree, but this doesn't contradict the existence of independent nature.
Of course not.
Also.
Of course not.
Yeah.
I said that there is nature, is capital N, which is out there. And that this nature is causally responsible for our perceptions, of course. Yes, but the mistake is to think that there is some sort of one-one correspondence between perceptions and things in nature with capital N. Nature with capital N does not filter through the perceptual system. Nature with capital N is elaborately by our perceptual systems in a pre-categorical level, without the involvement of reason. I say something that philosophically, challenging. To perceive is a way of thinking. Yeah. To perceive is a way of thinking. We are already thinking, we are perceiving. And this is an important thing.
I think you find it in the car.
Yeah, well, he's right. He's right, yeah.
Well, you have some like passion is the way of speaking.
Yeah, yeah.
If I can echo, it was mentioned by Einstein that if you have a physical theory, for instance, it should describe nature, but also what we perceive about nature, including all this process that you say thinking. I agree with that, but thinking, the way we perceive, the way we think things which are in the independent nature is part of the physical theory, so it's also described by that.
Yeah.
So I don't see what is new in that.
No, it's not new. I'm not saying that. I'm just trying to make it clear, things that everyone should see. No, it should be obvious. I mean, it should be obvious. I'm trying to make things that should be obvious, right? If you think it's obvious, I fulfilled my goal.
Yes,
right?
but,
it is obvious, right? It is obvious. But Wiener doesn't think that. Well, Wigner is a Nobel Prize in physics, and he can't see that. So we have to do something about that, right? He can't see that. In fact, as history shows, when you get tired, you just tell me, then I should summarize the rest, okay? In fact, as history shows, the true object of physics, at least from the 17th century on, is not primarily perceptual nature, but a mathematical substitute of it, which I call physical nature. Regardless of whether perceptual nature is already bears the imprint of particular human forms of perceiving, or else whether perception simply mirrors nature, the fact is that we perceive patterns, forms, or structures in nature. Whether some of these structures, at least, are contributions of our perceptual systems in the processing of the electrical material coming from the senses, or whether the structures we perceive are all intrinsic to nature, the fact remains that we perceive structures in nature. And who says structure says mathematics? Mathematics is the science of structures, either freely conceived or intuitively presented to consciousness. The creation of mathematics as an intellectual endeavor so early in human history testifies to the ubiquity of structures in human experience, our capacity to consider them abstractly, and our willingness to invent more. Some perceptual structures stand out so conspicuously that they invite mathematical investigation. For example, the proto-geometrical and topological structure of a perceptual space. There's something funny here. When you call about perceptual space, if you hear a physicist talking, as soon as he mentions the space, it's, oh, space and points in space. There are no points in space. Space is not made of points. No one has an experience of points. This is clearly brought out by Weil in his book, Das Continuum. Space, intuitive space, is not made of points. We atomize space as an idealized representation, which is mathematical. That's why we can deal with space with our geometry. Our geometry presupposes points and sets of points. All the things are not in perceptual space. They are only in mathematical space. But more often, the patterns that we perceive in nature can only become fully mathematical by being idealized. Perceptual space points only admit a geometrical structure proper, including a metric structure, after being idealized into a manifold of mathematical points. Privileging structures of experience that admit either directly or upon idealization mathematical treatment was a novelty introduced in science at the beginning of the modern times, Galileo, Descartes, and Newton, among others. This radically changed our concept of nature. Physical nature, a mathematical manifold accessible only to mathematical reason, replacing perceptual nature as immediate object of concern. Two intentional acts stand between perceptual nature and the concept of nature of modern physics. Abstraction, which brings relations and correlations, that is, form instead of content, to the focus of scientific interest, and idealization, which makes forms discernible in experience, in perception, into mathematical forms properly, thus reducing forms which are actually perceived to rough approximations of supposedly more real mathematical forms. The matter of perception, stuff like sounds, colors, etc., however, is not simply dismissed, but given objective representatives in an overall scheme of causations and correlations reducible to mathematical determinations. Color, for instance, among other secondary qualities, are taken as mere subjective impressions caused by a determinate type of radiation that shows up in the explanatory scheme of science as a mathematical field filling empty space and characterized by a set of mathematical parameters. Let's now briefly consider the presupposition that nature is submitted to laws. Obviously, no amount of evidence can count as either a proof or a disproof of this presupposition, so it cannot have the status of scientific hypothesis. Particular natures can be hypothetical, but the presupposition that nature abides to the rule of law cannot. And if not hypothesis, what then? The answer is straightforward. The lawfulness of nature is also a component of the intentional constitution of our scientific conception of nature. It's how we conceive nature to be. The presupposition stands no matter how often we're disappointed in submitting nature to laws, simply because the science depends on it. In physical nature, the laws of nature are, of course, mathematically expressed, and the concepts for adequately expressing them often require mathematics in an essential manner. The examples are lesion, instant velocity, entropy of fields of different types, scalar, vector, tensor, observing point mechanics, etc., etc. So what I'm saying here, that it is an intentional component of our intentional construct of physical nature, that physical nature is submitted to laws. This is not a hypothesis. It cannot be a scientific hypothesis. It is an a priori law. An a priori law can only be understood in terms of intentional constitution. That's how intentionally nature is supposed to be. By ignoring the intentional process involved in the modern conception of empirical nature, and by reinterpreting the historical development of this process as the unveiling of the true nature of nature, Galileo appeared in the process not only as inventor of a method for investigating perceptual nature, but as the discoverer of a truer nature behind the given perception, only accessible through mathematics, the famous Galilean metaphor about the book of nature. Wiener takes by a given what is a product. The mystery of the applicability of mathematics in physics derives from this identification. Obviously, mathematics must have a major role in the investigation of the mathematical manifold that physical nature is conceived as being. But insofar as one sees physical nature as a given and mathematics as a product of human culture developed for the most part without paying particular attention to how nature is, one is inevitably faced with a puzzle. In fact, the applicability of mathematics in physics is only an aspect of a more general logical problem, interested in itself, that of the applicability of mathematics in mathematics, which boils down to the logical problem of how different structures and their theories relate to each other. I'm going to summarize the rest. Then the point, to make it in few lines, mathematics is the structure of nature. Mathematics is the study of structures. Physics deals with a certain type of structures. Those that are idealized as representing structures given perception or mathematically enriched for theoretical purposes. Then I have on the one side a science which is devoted to a certain type of structure. On the other side, the general science of structures. Is it a mystery that one has a relevance for the other? Of course not, right? It's not a mystery how one can be used in the other. The applicability of mathematics in physics is only a chapter of the applicability of mathematics in mathematics, which is a very common phenomenon. And we all see this as obvious. There's absolutely no problem that, of course, mathematics is used in mathematics. But we find puzzling that should be used in physics, as if physics were not in some sense mathematized to the point of becoming, on a theoretical level, just part of mathematics. Now, I consider the phenomenon of applicability. There are many ways that mathematics can be applicable in physics. First, as a tool for drawing consequences within mathematical theories of nature. This is, requires that nature has been mathematized. So theories of nature are mathematical theories. This, as Wigner says, is a straightforward use of mathematics in science that was no problem. Of course, I can use mathematics to derive consequences within mathematical theories. Now comes as an essential conceptual instrument for the formulations of laws of nature. And this is funny because this is how mathematics becomes master of the field. And then Wiener gives a lot of examples, like Dirac formulation of the laws of quantum mechanics. Of course, that mathematics must have an essential role for the formulation of the laws of physics. Of course, because the laws of physics, the supposed laws that regulate the behavior of physical entities, in fact, are mathematical laws relating mathematical representatives, right? And then, since I decided to deal exclusively with mathematical representatives of the formal aspects of perception, of course, I just oblige myself to make the laws that I want to bring to the light, which are mathematical laws. I oblige myself to use mathematical concepts. And then I skip the examples he gives. I analyze some examples. And I also, what I do in this sequence, is to analyze some particular examples that Wiener gives. For instance, Newton's laws of gravitation, how appropriate Newton's laws of gravitation is. And here there is an interesting point. Wiener says it's very, very interesting how accurate certain mathematical theories of nature can be. For instance, Newton's law of gravitation relied on a very, very, rough empirical basis. But as soon as we could improve our observations, we realized how accurate the theory is. Well, the thing is that accuracy does not count as a sign of truth. And I give here even Wigner recognizes that. I give here an example. Of Ptolemy's scheme. You know, if you take Ptolemy's scheme, which we consider to be inadequate, if not wrong, inadequate, can be by using of enough adjustment, can be suitable for explaining a certain range of observation accurately beyond any possibility of finding.
But what do you mean it is not true?
No, it's not. It's not our official science any longer.
No. I think it's my mistake. If you say there are kind of fictional entities, right? The circles.
But they're not fictional. They are just mathematical.
No, I would say, and actually Ptolemy himself, he would claim he was not realist, right?
Yeah.
He would claim
Yeah.
they really exist or something, right?
Yeah.
But so you can say he was wrong saying that they exist, but you can say he was right making accurate predictions. So,
Yes, of course.
So it's not the wrong theory.
No, it's not wrong theory. In this sense, it's not a wrong theory. In the sense of making accurate predictions is absolutely right. It's wrong in the sense of representing in the most adequate way how nature actually is. Right? This is
something that theory does not. It would be wrong to say it does it wrongly. It simply does not.
Does not.
Yeah.
Does not. Yeah. It's wrong that it does. It's false that it does.
By the way, it is not essential for the discussion, but it is wrong that with Ptolemy's theory you can reach a good precision. And this was already wrong and recognized by Kepler and Tycho Brahe.
No, it's
impossible to make
it's not a good precision of the whole range of phenomena, but if you narrow the range of phenomena well enough, you make adequate precision. Well, that's what
it became completely wrong. No.
Yeah, adding a
cycle.
cycle.
You cannot model ellipses by adding epicycles.
Well,
No, it's different.
No, but you can approximate. You can approximate, can you? Well, at least my sources is you can. For instance, there is a paper here.
When Kepler discovered the ellipses, and for that reason, this was a big surprise for him and a big disappointment also, because he was expecting something which could be in some sense an approximation.
What Julius Barber says was that you cannot empirically distinguish ellipse from just moved circle, just a circle with
No.
There must be.
It took 3 years for Kepler to recognize that, but this is completely different, in fact. And he was expecting not to find an ellipse. He was expecting to find something.
Of course, but
this is out of the discussion. But
but there is a quote here that I'd like to read.
In that sense, excuse me, in that sense, the Ptolemaic theory
is wrong.
And even if it works at some approximation, the fact is that if you have a new experiment, you should go to a higher level approximation. It's something which is at the same time empirical and fundamental difference. So
Yeah.
this means wrong means that, in fact. if not every theory is right at some level. So you have
Well, we can argue for that any theory is right up to a certain level.
yes, okay. So this is tautology.
Yeah, but my point is a general one, that you cannot infer from accuracy of predictions in a descriptive sense, in a strong sense, having to do with some ontological facts, hard facts. Yeah.
If you take Newton and Einstein, for instance, there is no way even in any approximation to account for eclipse data or for Mercury orbit with Newtonian theory. Absolutely no way. So in that sense, it is wrong. And the corresponding description of the world, you must abandon it.
But this is not the point. The point is that even if it is accurate, I cannot infer the truth.
Sorry?
Even if the theory is accurate,
yes,
to the as far as we know, we cannot infer that is the true theory.
Oh, okay, true has no meaning, but if you want to give a meaning, it is you cannot say that the theory is true, but you can certainly say that it is wrong. And
yes.
this is the case for
Well, I think let's go with that. Wigner's point is that the mystery lies in how accurate the theory is. And then he derives a conclusion, more or less, not explicitly, but derives the following conclusion. This means that mathematics can uncover secrets of nature. Otherwise, how can you explain that a mathematical theory can be accurate? My point does not follow. It's a non sequitur, right? This is a non sequitur. I'll say, and then he says something interesting. See, Newton's law, this is Wigner, involves highly non-intuitive mathematical concepts as that of a second derivative. Then he derives the conclusion. Then somehow second derivative must be part of the fabric of nature, right? This, of course, this is not the case. I use a second derivative because I'm dealing with a mathematical concept, which is, as I explained already, at least 3 steps far from nature herself, right? Then I say, the fact, however, is that this notion does not have anything to do with our intuitive perceptive experience of nature, not only with mathematics, only with a mathematical surrogate of it. Mathematical concepts do not apply to nature as perceived, only to nature as intentionally conceived. That is physical nature, an abstract, idealized, and often mathematically enriched version of the former. Now there is some, I think there must be other examples. Let's see. Let's talk about, I just skip this. The most relevant fact to be noted is that mathematical laws can only express formal structural properties of their domains, which, remember, are mathematical domains where certain features of experience can be represented, but only in idealized form. Mathematical laws are formal laws. As Hermann Weyl put so candidly, mathematics can only express what is most superficial in experience, its formal properties. He says that in Space, Time, and Matter, which different domains of experiences can share. It is a trivial fact that even radically different contexts can have the same or similar formal properties. So, there is no a priori reason why particular mathematical domains cannot, 1, represent the other aspects of the same realm of experience for which they provide adequate representation, or 2, be formally similar to other mathematical domains representing different realms of experience. Then, I don't want to tire you anymore, but I consider the last example that I leave it for you to read if you feel like it. An example that's given by Steiner, Maxwell's discovery of displacement current. Steiner has an analysis of, in a paper he published, how this was a purely mathematical discovery. how, by using mathematical manipulations, Maxwell came to discover the notion of displacement current, which is not current at all, current in the sense of conduction current. But when discovered by Maxwell, introduced the consistency in the equations, consistent with the principle of conservation of electric charge, and opened the way to the discovery of electromagnetic waves. And then he goes into this example. I analyze the example, and I show that Steiner analysis is completely wrong, and there is another way of making sense of Maxwell's discovery. First, once Maxwell was first, even if the notion of displacement current was discovered by mathematical manipulation, there was a principle over rule in the process, the principle of conservation of electric charge. Then what he did was to find the mathematical expression of this principle in the system, in the mathematical system of equations, which is not simply playing with mathematical symbols, is find the mathematical consequence of a presupposition of a physical nature, right? But the fact is that this is not how Maxwell arrived at this notion. He arrived at this notion to work as a mechanical model. A mechanical model. And why working with a mechanical model functions? Because we have a situation of a formal similarity, of a formal isomorphism. Then this explains, obviously, why he could work in a model, find things about something that had nothing to do with that model. It's a matter of a formal similarity. And Maxwell himself recognizes that. There is a quote here from Maxwell. Here, the footnote I noted 20. Maxwell is quite clear about the purely formal relevance of his mechanical model. He says, the conception of a particle having its motion connected with that of a vortex by perfectly rolling contact. I have to explain that because his mechanical model considered vortices and the electric charge were certain wheels between these vortices. And may appear somewhat awkward. I do not bring it forward as a mode of connection existing in nature. It is, however, a mode of connection which is mechanically conceivable, and it serves to bring out the actual mechanical connections between known electromagnetic phenomena. This is quite interesting. Then what Maxwell was thinking, he said, well, electromagnetism has mechanical effects. What sort of mechanism would have the same effects? Then he would reason by formal analogy, right? And then I analyzed this example, and then I think I came to the conclusion. There is some, I analyzed carefully the example. If you want, you can read the paper afterwards. But I think I came to the conclusion. Now, I think that I can already conclude. My point is that the supposed mystery involved in the applicability of mathematics in physics, in any shape or form it takes, particularly as a heuristic instrument, which puzzles Wigner and Steiner, is in fact a pseudo-problem rooted in philosophical particularity. The authors take a realist stand with respect to the question that prejudges the issue. They confound the physical nature, a somewhat simplified and idealized representation of certain aspects of perceptual nature, those precisely that can be given mathematical expression, divides for methodological purposes with nature herself, taking for a given what's only intentional construct. Perceptual nature has, of course, already, to some extent, a mathematical structure, simply because we perceive nature as a structured systems, and mathematics deals with the structures, be they materially instantiated in given systems or emptily conceived in abstract. To suppose that the structure perceived in empirical experiences belong to nature out there, existing independently of perception, is a philosophical thesis. We have no reason to accept them critically. But even if they are indeed independent of the action of perceptual systems, perceptual structures are usually mathematically too poor to invite a more sophisticated mathematical approach. In general, only by the action of idealization they become full mathematics. By idealization, perceptual nature is turned into physical nature, a mathematical manifold, which obviously invites a mathematical approach. The raison d'être of the whole process, Mathematics is intrinsic to physical nature simply because the physical nature is tailor-made for mathematics. As any mathematical manifold, physical nature can be further enriched mathematically, inviting even more sophisticated mathematical treatment. This alone accounts for the risk efficacy of mathematics in physics, in no measure different from the efficacy of mathematics in mathematics itself. But if in mathematics, mathematical facts stand no matter what, in science they require being interpreted as phenomena in perceptual nature and empirically verified. No mathematical indication of hitherto known phenomena, which invariably occur at a purely formal structural level only, can count as an outright discovery of anything in perceptual nature, independently of, first, being given a material content, either in a previously determined content or a new one, and being effectively perceived in the context where its mathematical indicator is interpreted. Material content, as we saw, is never predetermined theoretically, and so scientific discoveries can never be only a matter of mathematical manipulations. Okay, thank you.
Thank you. That's all the discussion. Is there any questions?
Very interesting. I have a lot of
Yes.
questions. This subject is very close to huge discussion between Humanian and anti-Humanian view of necessity of laws. Could I
Yes.
make some picture? As I understand your picture, if we put our mind, our consciousness, and around nature with big N.
Yes.
And here we have many filters.
Yes.
Yeah, many filters. And we perceive nature from these filters.
Yeah.
Yeah? For example, let's for these filters refers to mathematics. There's another filters, for example, religion, mystic, social opinion,
Prejudice.
common sense, many other filters.
Idealism.
Yeah. Okay. And from each filter we get some picture. Yeah.
If you want to use picture, yeah, okay.
Some projection. And this perception.
Yeah.
And this reality that we conceive.
Yes.
Yeah? And your idea that if it is, for example, Newtonian mechanics, this theory of field, or this relational principle, this quantum mechanics, and we see this different picture, and it's not surprising that this picture coincidence with our mathematical way of thinking. Okay? And there is some coherence between our way of thinking and the result that we achieve. Okay. The question is, if okay, I agree that this result has a source of our way of thinking, but from this you make some concept that in this here there are no
laws, there are no structure.
Yeah, I don't know.
Because all structure of intentional structure, they are only here.
No, well, I would make a more complicated scheme. You know, I would make a more complicated scheme. Let's suppose this whiteboard is nature out there. Okay. Well, I mean, the, almost the entire board is nature out there. Then I'm isolated a section of which with, let's say, myself. Okay, and I have two layers of filters. Let's call them filters. I have one layer of filter which are the sensorial perceptual systems. Okay, they are the sensorial perceptual systems. And this layer, yes, yeah, when they are there, sensorial perceptual systems. These systems are already acting in order to make sense of inputs. They are acting in order, they are not just windows through which the inputs go through. They are not windows, right? They are active systems. And these systems are elaborating somehow, let's call them representations. The word is not a good one because representation seems to be a picture of something that stands out there. It's not a picture, it's an elaboration, okay? But this is only the first level. We have another level, which is our cognitive process, or our reason, let's put it. Then it comes first level perception, sensorial perception. Another level is the categorical, the pre-categorical, this the perceptual, and the categorical, in which I categorize, I reason, right? And then I reason according to certain categories also, and which, in case of physics, involve the process of abstraction and idealization. Abstraction means isolation, basically. I do not consider, physics does not consider all aspects of perception, but only the formal structural aspects of perception. And then there is also the idealization process, which moves from a certain given to a mathematical expression of that. Then, after these layers of filters acted, what I have from nature out there is a mathematical structure, right? Then this mathematical structure is a construct. What is the mistake of Wiener and others, which is a strong metaphysical thesis, that these filters are not filters at all. They're just windows. And these windows let nature flow in, and everything we get here is just nature herself, right? This is the mistake. This is the philosophical.
But then, if I accept this basis for this picture, I think what is missed here is social level, because neither mathematics nor physics, even if divided, it's human. But it's human, social, and collectively.
Yeah, well, but I'm not going into that because this is dangerous. Because then you men fall into certain things that I find a bit crazy. You know, that saying that I don't think that nature is a social construction. I'm not saying that at all, right?
No, I'm not. I mean neither. But if we somehow anyway, then I'll make my own comments. Yeah, I also have more kind of naturalistic picture. But even if we somehow relate it. Nature, the as we would call it, human cognition and perception.
Yeah.
I think that's important. That it's this kind of traditional Cartesian way to just think about it in terms of individual. But I think that we necessarily need to put in kind of.
Well, I think when I say I'm not talking about individual. In fact, I'm talking about the community of scientists, which because our picture of nature is not an individual creation; it's a communal creation. There is an institution of science acting and actively involved in this.
There are many individuals with the same philosophy. And the same in intention structure.
Yeah.
But this intention, they are only for human beings.
No, not necessarily. Not necessarily, but it is thinking that.
And why this intention structure is are so similar?
In humans?
But it's collectively developed. It's not, I think that's
Evolution,
kind of
yeah?
Yeah.
Evolution.
If you say it's similar, right, it just you assume that it's independently developed in individuals and then they discover it's similar. But I think it's wrong picture. It's developed collectively. And those who not, how say, manage to join the collective, they just marginalize.
Yeah, well, I think we could go into that, but I want to restrict my perspective in order to get things clear. I think that it is the role of the philosopher to be first honest and secondly very clear, and try to get precisely what are the issues and to get precisely characterizations of the concepts involved. Otherwise, we just get ourselves lost in confusion, And then that what I'm trying to do first is to show that there are presuppositions in certain obvious views. There are presuppositions, and if you want to be philosophically honest, you have to bring these presuppositions out and analyze them, and we'll look at them and see to what extent they are justified and why they are justified.
I have actually two comments, if I may. First, I can look in a way. I'm very sympathetic. I also think that it's just somehow wrong, but yes, it made us good service. This paper that we're still discussing, it was written. It was on the 16th, 19th.
Well, it was a provocation. It was a provocation.
So it's kind of provocation.
It is a provocation. Yeah.
But so I absolutely, of course, agree with. We should give an answer. But one thing, and general strategy, I think, it's nature like also cannot see really other. So we should somehow explain how mathematics works and how physics works and discover some common, background. But on the other hand, I'm not quite convinced. I don't think that you took this as you told us, right? The transcendental
idealist. Yeah.
way. I think that may, perhaps, yes, you could give counter argument, but as far as I can see, it may also work if a similar actual strategy, but if you put more weight and more accent for kind of naturalistic explanation, right? I mean, you would say that the structure is imposed by us, by this collective or individual human subject, but say somehow it's in the nature with big N, and we as a part of this nature with big N somehow just inherit it and share it, perhaps, and we are active in that respect. It does not mean that we're just part of nature and we interact with other parts of nature, in particular for our practices and things like survival, but also in very special practice which we call science and which is related, of course, to technology and that kind of thing. Okay, that's the first thing, maybe. And second, actually, it's more specific. It concerns like notion of structure.
Okay.
And for the second thing, no, again, this general strategy, I think is reasonable. It's like Michael Resnick, for example, right? You know his book.
Which one?
Michael Resnick.
Yeah, I know Resnick, but which book?
It's called, but you say mathematical science of structure, you would use word pattern.
Pattern,
but his strategy was the same. Pattern is something which
it's
kind of share. But my observation about this way is actually it's quite specific, because this idea of structure is actually based on very specific way of conceiving of mathematical, making foundational mathematics, say represented by Bourbaki. Something that yesterday in my title, cement, even if you use this Bourbaki notation, right? Right. And it's a way to look at mathematics that philosophers like to the Resnick, maybe you, right, kind of extend on all mathematics, which is which works somehow, but I think that there are at least other ways to conceive of mathematics, and maybe in some sense they could make more justice to, and to also to that problem.
Which
and
is?
In particular, that concerns this problem of objects, right? You say mathematics, but objects in relation, then you say object is somehow cannot be fully.
Yeah, object is anything. Objects for mathematics do not matter. Any
No,
object is a
yeah,
mathematical
exactly.
object. Any object is a mathematical object.
Yeah,
Anything.
but not, no, I would say not that. Because you say mathematics invents structures, right? I would not really deny that, but I would say mathematics invents objects.
Yes, of course. I do not deny that.
No, but not that sort of unstructured.
No, listen, mathematics invents, I agree with you, mathematics invents objects for the purpose of instantiating structure.
No, I would say more than that. Because if you remove that, it's going to be specific. But
Can I go to the bathroom? Can I go to the bathroom and say? No, just a bathroom. I go to the bathroom and come back. Can I?
Okay, good, because otherwise I don't see.
Sorry.
I got questions.
Yes. I'm sorry.
No, I don't receive the answer about the
Attempt to create a new statistics. Yes.
Okay. Немножко. Пора заканчивать. Да, но это мы можем еще 10-15 минут. Тему не можем тогда начать. Отвергнемся с матчем. Да. Так. Да, все-таки все записывается на YouTube. Я страшно гордо освоил эту технологию. И когда довольно просто. Правда, качество картинки нехорошее, потому что не хватает скорости.
А он чего? Записывает тоже по кадрам?
Ну как вот экран все записывается.
Просто как кино он записывает.
Не, ну можно на камеру переключить. Ну,
тогда уже звучит как кино. А здесь показывается только презентация, но уже
да.
не кино, да?
Там есть более сложное, я еще не освоил. Можно несколько этих стримов, как это трансляция, их там миксировать потом. Так,
да, я видел такие, да, там, типа, в окошечке, там, иногда слайды, а в окошечке картиночка.
Потому что все это вот абсолютно бесплатно, доступно. То есть то, что раньше только могли там телевизионщики какие-то делать.
Но все-таки, если вы будете публиковать, лучше обычным путем.
Ну да, ну смотрите, с публикацией, вот что публиковать, вот просто там тексты, а тексты тогда, хочется же публиковать, чтобы это как-то было там рецензируемо, где-то не просто вот отпечатать. И тут надо тогда вот, лучше, чтобы мы заранее посмотрим, может быть, действительно шпрингеры лучше тогда, наверное. Они, в принципе, берут все эти вещи.
Куда шпрингер?
А?
Куда шпрингер?
Ну, какие-нибудь ноутисы, вот,
нет, ну, здесь можно отдельный софтвер.
Так они делают это. Если мы готовы. Ну да, нас нужно. Нас мало. Самый такой.
Sorry, it was nature making herself.
Yeah, so look, what I think. So the thing is that this structuralist conception of mathematics does not have interesting notion of object.
No.
Okay.
No.
Unlike more traditional mathematics, what Kant, for example,
Yeah.
considered, which,
Yeah.
like Euclidean geometry, does have,
Yeah.
interesting.
Yeah.
So, what I think that, at least this homotopy type, but I don't think it's specifically based on that we may have interesting notion of object,
Okay.
even in today's mathematics. So
Okay.
this idea somehow to put all weight on structures and somehow make objects uninteresting, it's not, put it at least it's not absolutely necessary, it's not the only thing to go.
Yeah.
One way to go.
Yeah.
And at least what I showed yesterday is one attempt to do that, to make a game. But philosophically, that would change a bit the picture, because again, we would say mathematics is not just inventing structure, which for reasons we now can explain somehow. Also, at least in some cases, as you put, just serve for natural science. But we would say something more. We would say that it invents objects, right? Which is, as far as we are talking pure mathematics, okay, those are fictionary objects and fictitious, but at the same time, it's very much connected to all our practice to make up material objects with our, industry, with arts, with apps, and all that kind of things. So we put more weight not only to structure, but just making these things up. But it would not drastically change the picture.
I know. You're right. Of course, you're right when you say that the structuralism in a way just get away with objects altogether. Objects are not an important thing, and sometimes in mathematics we feel like we are interested in certain type of objects. This is numbers. I want to understand the numbers, and not something that behave like numbers, right? And you're right about that, and this is a concern of mathematics. But this has changed things drastically, because even if I consider that mathematics does create objects, and these objects somehow interact with physical objects, this is also true. Then the interaction, it happens in the level of the theory, and this interaction can be understood formally, abstractly, structurally.
No. Of course, somehow when I say mathematics by that object, it's not like the outcome is really, individual, actually. The outcome is a form, but not form as a structure, but constructive form. Form is a system of rules.
Okay.
It's closer to Kant.
Okay. I can go along with that. I can even
algorithm.
I can even consider the notion of a formal object, for instance. I tried this, and some structuralists really got lost in this completely, because when they go and some structuralists think that the structures are in fact patterns involving abstract objects, and then they get all sorts of confusion when they try to identify these objects. How you identify them? How do you identity, for instance? How to define identity between things that do not have, are not individuals, they're only identified through their role in the system. Then they get involved in all sorts of confusion. And then I asked myself, maybe we can go around this problem by just not treating structures as systems of formal objects, but as abstracts that are always either instantiated, or just abstractly conceived by certain types of theory. Okay? Then I avoided this. Of course, what I presented today is just a rough sketch. It's a rough sketch. Fortunately, I was, the Synthèse collection, don't you? The editor of the Synthèse collection, just 2 days ago, invited me to write a book on this.
He changed recently, the new one.
It's Ottavio.
Yes.
Ottavio. Ottavio wrote to me. What? Yeah, he invited me to present his book. I said, I'm going to give you this. Are you fine with this? He said, oh, I'm fine with that. I'd like to see this. Then I said, okay, I take this opportunity, since I'm talking about this subject, to extend this into a book. And then my plan is to develop these ideas in a much, detailed way. Then you have the opportunity to criticize me with more details, you see, with more detail. Because this is my plan to, of course, there are certain problems here that I have to deal with, and I think to characterize the structures in a way that, avoid the usual problems that Resnick and Shapiro have, trying to avoid the problems they have. But also you mentioned Bourbaki. In fact, the notion of structure in Bourbaki comes from Husserl. The origin is in Husserl, and the Bourbakians, like many French, they were quite familiar with Husserl's philosophy, in fact. And they never say explicitly, but I'm almost sure it does. A friend of mine wrote a book recently showing that Carnap derived some of his view from Husserl by attending Husserl's lectures and never mentioning it. Never mentioned he attended Husserl's lecture.
Naturally, but for Bourbaki, I don't know. You think someone from Bourbaki
No, I think the idea of structure in Bourbaki is so. Is Husserl.
No, but there is more direct connection, and this is Tarski.
Tarski?
Yes.
I
mean the whole idea that you see this axiomatic method in its logicians who just doesn't work as I guess. But you need some.
This is not important. This is not important. But what I'm saying is that my inspiration is not Bourbaki. I do not derive my ideas from the Bourbakian.
But you use it when there.
I use the notation because it became completely standard. The notation became standard. And in logic, you use this notation. In algebra, you use this notation. So it became standard. But I do not derive my ideas from them. Although I recognize that they are the Bourbakian project, I recognize that as an actualization of some idea. Maybe there was no direct influence, but the idea is that Husserl's idea of formal ontology. It is part of Husserl's idea of formal ontology, a study of abstract structures in their relation to each other. Yes. No, of course not. Of course not. Yes, of course not. But mathematics is part of is an identity science, and it is part of formal ontology. And his idea of formal ontology is to study certain forms, to identify original forms and how they combine, which is a Bourbakian idea. See? Then it's very interesting that there is at least a theoretical level connection, even if there is no historical connection. So,
more questions or comments?
Are you going to eat?
Well,
I have comments, but maybe I will say on the round table.
yeah.
Okay, good.
Thank you.
Thank you. Now you can delete the paper, can read the paper, can do whatever you want.
I just have an interesting answer. I'd like to ask you if it's possible that some external structures or external laws exist that would be some kind of sources of our intention.
Of course. This thing here must be completely structured, and this structure may be filtering through. But how can we tell? How can we tell? It is possible.
Could we investigate?
Yeah, but how?
Could we ask this question?
You can always, well, how good it is. So we got this, but this is a reduction. If it is a reduction, then this can be
I agree.
stretched out.
I think it is necessary that something be that could be before and could be the reason this intentional structure.
Yeah, I think yes, it could be, but we could even ask ourselves, well, let's imagine how this would be. Maybe this is a rule for metaphysics, but it's not a rule for physics. Right? Maybe this is a metaphysics.
I say that there is the same discussion between okay, I agree that you want to right, but it's only part of the truth. It's only part. Okay, this is our intentional structure, but for me it's interesting to investigate.
Yeah, well, it is. It is. And I think, well, this is the role of metaphysician.
Yeah.
The metaphysician must think about it.
Yeah. Okay.
So then we see that the metaphysics must be a complement to the physics problem.
Зависает. Сейчас, ну ничего. Очень много забирает это прям транслирует. Ресурсы, такая там большой счет.
Yeah, I работает. Interesting, possible, and useful.
I said yesterday about semi-realism. Between Humanian view and anti-Humanian view.
Good. So, are you writing Fabio's book?
I actually recently published a book there, but before I signed it, called Category Theory and Semantic Measurement.
I think I saw that. Yeah.
But then I met him, he also told me.
He told me that he was here.
Yeah. So you know him well?
Oh, yes. Yeah,
okay. Great.
Will you send me your email like this?
And also you have to give me the address that your
Okay.
Oh, you just send me by mail.
Yeah, sure.
I'd like to, because I travel a lot.
You mean my CD?
Yeah. And I'd like to have your answers that I can hear. And also, I'd like if you could send me the book you just published online.
Это моя, да?
Да.
Моя, это папка должна быть.
Как называется?
А что-то так и называется, папа, механика.
Значит, внизу что-то. На русском, да?
Не помню. Вот здесь, по-моему, было что-то такое. А папки, и папки внизу все.
I'm going down. Okay. Слушай, я думал в Дом ученых сходить. Это немножко дальше, но там хорошо. Ты что, как называется? Отведешь? Отведу.
Нет, я просто... Папка, она называется так и есть. Там презентация, Quantum Mechanics, Foundations.
Ну вот смотрите, где сейчас папки мы прочитаем, все вот, наверное, новая папка. Презент, нет?
Да.
Ага.
Вот, и презентация отсюда взять.
Так, вот это, да?
Да.
Окей.
И можно еще взять, как бы, тезисы. Они есть у вас эти?
Ну это вы мне прислали, да. Это
вот их, чтобы я их, может,
Да? Ну, вот скажите, я тогда сам, ладно, найду, чтобы... Так.
Может,
Ну, вот единственное, сейчас открою, потому что я же вот говорю, у меня это самое... Только вот это Open Office. Ну, я надеюсь, что сейчас прочитать нормально.
Ну, можно точка, можно словом.
откроется?
Еще посмотрим.
А, так уже открылось.
Ну, это пока еще программа, сейчас посмотрим все.
А вот это мы забыли.
Да не, ну сейчас откроется. Сейчас. О,
О,
ну нормально, да? Вью там. Сейчас.
ну, надеюсь, что пойдет вниз.
Бывает. Вот он.
А как переключать вниз? Просто вот сейчас.
Ага. Ну вот так. А. Ну вот видите, говорю, у меня тут вот немножко вот он дурит.
Ну, ничего.
Они эволюция Вселенной меняются. Да. Это такое, да. Нет, как бы вывод вполне как логичный.
Чего, это можно взять, да?
А, да, сейчас я ее это самое.
Это
Чтобы достану.
длинная интервенционная вселенной. Почему вообще закон, да? То есть вот антропный принцип, он выводит вот это вот нет, и математически тоже. Вот он как раз говорит, что вот во всех этих там пузырях, да, могут быть какие-то законы,
Ладно, пока
как
туда... Пусть, наверное, отдохнет.
Я могу
по-моему, оно про математику.
Ну, вы можете... Видишь, у меня вот стирать, да. У меня здесь еще это самое. Он еще есть.
Ответ нет, потому что законы шахмат. Но есть наверняка какие-то другие законы, на которых эти законы шахмат опираются, ну, более высокого уровня, которые были там. Научный поиск заключается в том, что
You can leave here stuff.
Take it, because in case I need it.
Ну, да, ну, пошли. А завтра? А завтра ничего не будет. Еще нет. Ничего не будет.
Привет, слушай, я там все-таки немножко в расписании напутал, когда печатал. У нас где-то в 4 там вот с чем-то начнется круглый стол. Ну, где-то час, наверное, уже мы будем. Так. Хорошо, хорошо. Давай, понятно.
Угу. Угу. Так, сейчас одну секунду. Здесь закрыто. Вот, ну не знаю, как нам лучше сделать. Как переходить на следующий? Ну или вот такой сделать, как сейчас. Ну это понятно, а дальше так? Ну вот, она правда какое-то время ведь плохо реагирует. Ну вот так нажать и подождать. И следующий немножко барахлит. Вот так, да? Да. Ну да. Ну здесь видите что-то. Ну там. Не забудь она вообще. Подожди, ну, вот дальше. Ну я говорю, он у меня с ошибками. Вот у меня есть PDF, что все работает. Ну сейчас. Да.
Okay, let us restart. So this afternoon we'll have a talk by Alexander Pechonkin from Moscow University, and after a break then we'll have a round table. So everybody, of course, invited. So please, Alexander will talk us about the foundations of physics and phenomenological reduction.
Also, in previous paper Husserl was mentioned, but another context. What the idea of this paper? Usually about quantum mechanics, people wrote about the interpretation of quantum mechanics, about EPR paradox or teleportation, so on. But this paper about mathematical foundations of quantum mechanics, not about the interpretation of quantum mechanics. No, the development of mathematical foundations of quantum mechanics. And what the point that I connect the search for foundations with criticism. With criticism, I consider this to be a critical procedure. I treat it as a critical procedure, but criticism here is a criticism of a special kind. And this criticism, how to reach presumptions, how to reach the fundamental principles of the theory. I think that this is critical procedure. This is a critical procedure, and this critical procedure, but this criticism of a specific kind. This is not criticism of which is characteristic for competitive theories or rival theories, where one theory theoretician said that the rival theory has some defect concerning prediction, concerning foundations, empirical grounds, and so on. But this criticism to find to make the logical structure of the theory better, to make the logical structure of theory better. But it is not so simple procedure, because usually current formulations of the theory look like natural, natural and justified. And to see some logical defect, we must overcome some stereotypes. And in this yes, I was said that it will be good after a while.
I think most of this shows correct, but in some cases there are things like this. Sorry for that.
Stereotypes.
I don't have
Stereotypes. And I turn to Edmund Husserl, and Edmund Husserl had such critical procedure which is named the phenomenological reduction. But phenomenological reduction is a rather specific criticism. This is not criticism of the rival theories. This is criticism to take theory in bracket to treat the theory like as if it is theory. And I can give an example. For example, in Russia, now is very popular the word self-organization. Self-organization. What does mean self-organization? This is increase of organization. This is tautology, but nobody paid attention to this logical break, to this logical mistake, because this word is so usual, so custom that nobody asks himself what does it mean really? What does it mean really? And many such words now exist in Russian philosophical language. I'm sorry to say, about which nobody asks what does it mean. What does it mean? The people say self-organization, post-non-classical science, and so on. But no question what does it mean. And what is the remedy here? We we should use turn to Husserl, Edmund Husserl, and use his methodology of bracketing or closing in inverted commas or of current beliefs. Of current beliefs. And after this, we can a space to analyze and clarify them. And I try to follow this line in the development of mathematical foundations of quantum mechanics. I take three steps. The first step in the development, as is well known, quantum mechanics arose as two theories, matrix and wave theory, and but the following development was development toward more rigorous mathematical foundations. The first step was Paul Dirac principles of quantum mechanics, then von Neumann book about mathematical foundations of quantum mechanics, and I took the third step. Third step, right, hypothetical. I follow here Hungarian philosopher who works now for London School of Economics, already, and he showed that von Neumann was not satisfied his construction of Hilbert space and tried to construct another structure of quantum mechanics, and he published several articles. For example, von Neumann's concept of quantum logic and quantum probability, soft axiomatization, John von Neumann on methods, and von Neumann's method in the physical sciences, And there is an article why von Neumann did not like Hilbert space and what he likes instead. What he likes instead. And therefore, we have 3 steps. No? But quantum mechanics arose, as I said, as 2 theories, matrix theory and wave theory, and immediately arose attempts to provide bridges between these 2 theories. And usually said that Schrödinger unified these 2 theories, but as Norwood Russell Hanson said, Schrödinger found only mutual translatability of these formulations of quantum theory. He says what corresponds psi function in matrix theory. Schrödinger showed that if we have a transformational similarity, the column vector of this matrix corresponds to this is not a simple problem because this is an artificial construction, but this is the central concept of wave theory, and Schrödinger showed that this matrix, this column, it corresponds to psi function in the wave mechanics. But this is not search for foundations. Foundations, this is I am late to explain what does mean phenological reduction, which I use. But I hope the picture will rise. No, it's hidden space. It is Derek. I need this. No, but I don't say anything new. I said only that Dirac constructed the concept of Hilbert space, and here distinguished between 2 methods, methods of representations and symbolic method. And he said his famous words that symbolic matter penetrates deeper into the nature of things. And he said also, very famous, words that the aim of physics, the goal of physics is not picture. If picture exists, it is good, but that is secondary problem. And in such a way, he received this space to construct his symbolic presentation of quantum mechanics, the theory of invariance and quasi-invariance of the transformations, and distinguish which can be realized in two ways, as matrix mechanics and wave mechanics. Matrix mechanics and wave mechanics. The following step is certainly von Neumann. Von Neumann criticized Dirac. Von Neumann, as is well known, said that Dirac insincerely admitted improper function, delta function. But what the matter? The matter that it is important to show that this criticism was not, if a person looks at Dirac's principles, I think he doesn't notice any logical mistakes. But von Neumann can go deeper, and he considered separately the problem of continuous spectrum and discrete spectrum. The thing is that Dirac unified quantum mechanics. He unified two formulations of quantum mechanics, matrix and wave. But if we look deeper, Dirac depended on the ideology of matrix mechanics. And on the philosophical language, we can say he depended on the ontology of discreteness. And here, this is quotation from Neumann. This is discrete spectrum. This is continuous. And to unify these two methods, Dirac admitted delta function, which had no good mathematical presentation at that time. And the third step in the foundations of quantum mechanics, but this third step, but this is regular definition of Hilbert space. One can find it in Wikipedia. The third step is quantum logic. Everybody knows the famous article Berghoff, von Neumann, where they developed the theory of non-distributive lattice. Lattice this is logical structure. But what does mean lattice? Lattice is a structure, partially ordered set. What does mean partially ordered set? That not every element of this set is ordered with respect to other element, but not every element.
With smaller stuff and
But yes, but if we take a pair of elements, they cannot be ordered. But if we take one element, we take the other element which ordered with respect to them. But this is here. Yes, but I'm sorry that technical difficulties arose, but I can explain what does mean. They change no, but it is quite clear for everybody who have an idea about quantum mechanics that distributive lattice is not good here, distributive lattice, because it is contradicts the principle of quantum mechanics. And they used another lattice which is named but this is modular lattice, but it is not distributive lattice, but it is more general property for this lattice is used. But the problem, I honestly speaking, I did not study this mathematics good, because this mathematics is rather specific. The problem was that for Neyman, we have now self-criticism. For Neyman, self-criticism. First, we have direct criticism of wave mechanics and matrix mechanics. Then we have the von Neumann criticism of Dirac. Now we have the third step, von Neumann self-criticism. Self-criticism, you see, von Neumann used in his famous book von Mises' conception of probability. And this results in many philosophical discussions. What is reduction of the wave packet? What is psychophysical parallelism? And I think that von Neumann, as a good mathematician, don't like these philosophical discussions. He tries to embrace everything and to put everything into the mathematical construction of quantum mechanics. Here, and what does it mean? How to define probability? He tried to define probability in Kolmogorov's style, but certainly not when sigma algebra was absent. And he tried to define this the probability, quantum mechanical probability, by constructed specific quantum logic. This idea of von Neumann, according to Rede, this was the second part of his work with quantum mechanics. This is construction of quantum logic and probability defined on this quantum logic. Usually, probability, Kolmogorov defined it. He constructed sigma algebra. This is a rather simple theoretical set structure, but this does not fit to quantum mechanics. And von Neumann tried to develop this construction. So I have straight line to increase of rigidity or rigorous presentation of quantum mechanics, But there is one problem. The thing is that Bogolyubov wrote in his book Bogolyubov, Logunov, Todorov that it is possible to provide mathematical foundations of quantum mechanics, nevertheless, by means of delta function, but we need only the theory, the rigid theory of this delta function. But I don't know if anybody constructs this. No, the theory of field, yes. The theory of field, yes. The constructor, Bogolyubov, Logunov, Todorov, certainly. But the problem of presentation of quantum mechanics separately, I have not seen any book. Therefore, if my picture is good, we have such good picture. Increase strict, rigorous foundations of quantum mechanics. But if delta function is possible to present in good way, this picture will be destroyed. Thank you.
Thank you very much. This question? When people thinking, maybe I ask first. Actually, I'm very concerned concerning delta function. I just said that, of course, when Dirac proposed it, that was something like today, Feynman integral is something that physicists do, but there is no strict mathematical foundation for the same thing. But such mathematical foundation for delta function was, of course, provided soon in 40s, I think, in 50s. In Russian, it's called обобщенные функции. That's Kolmogorov that. In the rest of the world, it's called distribution. It's the same thing. Yeah. So look, at least that part is done. I mean, mathematical part. But you mentioned physical part. Yeah, that's all for me. So, or at least I don't know.
Yes.
Yeah. But my question is.
But this is corresponds to my scheme.
Yes. But the question is that you mentioned actually was in the title there of this write-off, soft axiomatization, right?
Soft axiomatization.
Yeah, and so actually, from historically, we may notice that these people like Dirac and von Neumann, they were seriously interested in logic, which is rarely the case today, right? Physicists would be interested in logic. And but even this Rigel and yesterday I quoted, you remember, from Mario Bunke, say logicians would not recognize this as logic, or at best they would say something like soft logic. But what do you think about it? I just wonder, maybe in here there is something more into it. So one way to look at it is say, yes, they're interested in logic, but they don't know logic really So they pretend to do logic, which is not really logic, something, right? Like this. Erudition criticize. Or perhaps there's something more in this attempt, something, ideas that magician cannot really grasp so far. What do you think?
Yes, this is really a problem because it is it is not clear what does mean soft axiomatization. Yeah, it is clear that Hilbert axiomatization of calculus of arithmetic is not soft axiomatization. This is real axiomatization, and we can go further because this is no more. Yes, but in physics we construct soft axiomatization, but this soft axiomatization is rather compromise. But I think my scheme is good for this concept of axiomatization because you see, this is constructed by means of criticism. Criticism is constructed, criticism of the logic, of the logic. Logical transparency, logical transparency of the theory. But in which way we see that there is a problem of this logical transparency? We must stay at meta position and provide something like Edmund Husserl did when he provided phenomenological reduction. That is to put this to change attitude, natural attitude, and take to set aside natural attitude to take phenomenological attitude. That is to see that this is text is flexible. This is text is can be guilty. Also, it can be taken as obvious, because you see, when Dirac constructed Hilbert space, it is obvious Hilbert space, and before von Neumann, as far as I know, and if I follow Max Jammer or Mehra, nobody saw any mistakes, any logical gap in his presentation of quantum mechanics. But when von Neumann look from, how to say, put in bracket the ontology of discreteness, he noticed logical gaps in the representation of quantum mechanics.
I think that, first I would like to say that I think that quantum logic is not real logic because there are no notions of logical implication or logical deduction in this science. This is my opinion. But I'm not sure that quantum logic was actually. Do I understand correctly that quantum logic from the side of von Neumann was maybe considered as criticism to his previous conception of Hilbert space? this some strengthening of the concept of Hilbert space or something like this. I thought previously that the mathematical foundations of von Neumann and quantum logic of von Neumann together with Berkov was developed parallelly, but not one instead other. Huh?
No, exactly the same. The first edition of quantum logic is in his book Foundation of Quantum Mechanics, and then he developed just one separate paper in a year. But it's true, it's just part of the theory.
There is a good book, Hooker, Logical Algebraic Approach to Quantum Mechanics. And in this book, really, the first article, Berkov and von Neumann, is rather illustrative. It shows that really we have no distributive lattice. This is, by the way, it is rather natural for the quantum mechanics. But the further the effort to construct quantum logic to that it will reach the level of the working the physical theory, not only illustration of logical specific of this theory, but the second, but the third step was, according to Redder, to construct quantum logic as a physical theory. But he wrote that von Neumann did not finish this work. He started but did not finish. He has many other duties. Yes, and this, but the problem was really, you see, everybody who read von Neumann noticed that there are philosophical chapters in this book. This is not natural for the book on physics. Take Landau and Lipschitz, for example. No philosophical chapters. And this philosophical and chapters arose because he used von Mises' concept of probability as a limit of frequencies. Limit of frequencies. Certainly arose the problem, the reduction of wave packet. If the reduction of wave packet implies the second problem which arose, which led to psychophysical parallelism. This is too much philosophy, rather vague philosophy for physical book, and von Neumann tried to escape. Too much philosophy.
Question? Okay.
Thank you.
We finished earlier, and so we may make, I don't know, 15 minutes break. 15, some 20, and then we resume. Yeah. решетки острова Бурятии. Ну, это старое. Ну, реально, да, я посмотрю. Давай сейчас. Так. Пусть пустит.
Сейчас буду опять бедного ребенка доставать.
Буду
опять бедного ребенка доставать.
Я трансляцию в YouTube делаю.
Да.
Да.
А ролики-то есть? Я бы вчерашний день посмотрел.
Смотри, все есть.
Да?
Ну там картинка очень плохо идет, но звук весь идет нормально.
Какое 480 разрешение?
Вот я, может, слабое поставил.
А, для скорости трафика?
Ну я сам выставил трафик небольшой. Может,
Ну, по 480.
да, ну я так поставил.
Вот мы как планировали семинар по кассиру, но было невозможно сделать это вместе. Давай,
Что?
меня зовут Рабич Евгений.
Да, очень приятно.
Да, потом личные обстоятельства втерлись, ну, у вас несколько месяцев назад мы планировали что-то вроде семинара по кассиру. Вот, может быть,
Да.
сделать какой-нибудь чекаемый, продолжительным или не очень будущем.
Ну, можно сделать кассиру, да. А где мы планируем? Я честно
Здесь синеока. Проводится синеока.
Вот это
еженедельный
Ну,
семинар.
давайте сделаем, отлично. Ну, я, правда, вот уже наездами только в Москву.
Так
Ну,
давайте
спишем.
я запишу, как бы.
Адрес, конечно.
Адрес уже есть, я вам отсылал письмо, вот, вы ответили уже мне, если посмотрите на электронную почту.
Да? Ну, напишите еще раз, ладно?
Еще раз.
Нет, ну просто чтобы насчет вот этого.
А,
И тогда договоримся, да, там, вот, на октябрь, ноябрь, да?
хотя бы.
Честно, ну о чем мы говорим-то? Просто как бы собраться.
Не просто собраться, наверное, что-то было серию каких-то вещей.
Ну, серию я особо сейчас подписываться не могу, потому
Ну,
что я
понятно.
занят.
Не, ну вяжемся, потом посмотрим. Что
Ну да, ну может быть. Это, да.
Еще ты на улице подожди, я факультет биологии, помню?
Да.
Предлагали.
Да. Слушай, ну напиши, ну сейчас вот у нас переезд, это вот последнее, что у нас здесь. Ну вообще обязательно возобновим этот семинар. Напишите еще раз, вот у меня это письмо, ладно? Спасибо, обязательно. Да. Да. Компьютер не хочу просто. Поэтому лучше наоборот, мне сейчас это попробую включить.
Мы куда, на 4 пойдем?
Почему здесь?
А,
Там уже все вообще разгублено.
я наконец-то выучился.
Я сейчас выключу. Ну давай текст это самое, мне присылай. А тут у тебя там какие-то великие проекты.
Я сначала напишу абстракт, потому что я решил говорить.
О.
Но я несколько дней где-то наперед.
Так.
Напишу абстракт, вот. И все переделаю и пришлю текст.
Он два тетрук. Так, сейчас давай-ка я найду.
Там много листов?
Ну, что посмотрим.
Мы просто можем распечатать те, где нужна моя роспись, чтобы...
Ну, естественно. Да не, она мне все равно нужна целиком. Пускай печатает. Так, даже...
А там бумаги хватит?
Ну, ой, а подточили еще бумагу. Ну, наверное, хватит, я думаю. Ну, возьму. Вроде как там не надо ничего это заверять, я так понял.
Если будет не так, то пусть лучше, они лучше описание прописывают.
Ага, и ты скажешь. Ага. Значит, смотреть, в чьих руках как бы власть. Они тебе не дадут все денег, и потом что, пойдешь в них жаловаться?
Маме
Так,
расскажу.
маме расскажешь. Так.
Это то, что по большим данным, да?
Да.
А я когда болел, я круглые сутки писал и перед сном включал себе на всю ночь документальные фильмы про Гитлера.
Ты попробуй, зачем тебе? Ты попробуй теперь все-таки сам немного, понимаешь, это надо, ну, хорошо, ты там писал в творческом порыве, но ты сам это структурируй как-то,
да.
и чтобы не я вот за это все делал.
Не, я вообще все это пишу...
Ну, как это, критически.
Ну да. Не, это да, потому что, ну, я уже третий раз все переделываю за месяц. А чтобы, ну, не было никаких проблем с прочтением, я это все пишу в духе Wittgensteina. Нумерую абзацы, потом тезисы, чтобы, ну, не было, ну, сложно подчиненных предложений.
Ну да.
Я их не люблю. А когда есть номер и, ну, подлежащее сказуемое, и есть такой набор, и, ну, есть некоторая структура. Поэтому я в таком формате это все буду делать.
Так. Посмотрим. Ну, там на одной только странице. То все идем.
Наверное, к концу.
По физическим геоцентам, Ковалев. Вот, Агузин.
Скажи, pardon?
Предоставляю бывшую родину Андрею Вячеславовичу. Вот.
Полностью, да?
Ну да. Ага. Ну и все. Подписывайся, число там поставь.
22.
22. Ну все, по-моему, там же, если бы надо было замерять, было что-нибудь написано, такое место для печати, да? Ничего такого нет.
Нет.
Ну все, отлично.
Ладно.
Ага, ну
Пойду сидеть с детьми.
Давай, удачи.
Да, спасибо.
Все, ну на связи, ага, пока. пишу понятно.
Я просто читал, нет, я читал ваш абстракт, что вы поставили, ну, просто я уже легче, да, так вот с нуля,
Что из-за математики и язык.
да, просто вот тут трудно состыковать в голове.
Нет, зачем трудно,
Я поэтому, я свою презентацию просто вот выложил на экран, да, чтобы параллельно можно было, потому что я понимал, что я тоже не всем будет понятно. Да, это потребовало, конечно, больше времени. Все-таки у меня остался вопрос. Нейман сам с собой как бы спорил, да? То есть он сначала у него было сознание, выполнение, да, потом нет, все-таки
Нет, конечно, здесь возникает вопрос. Очень многие буквально очень любят все эти и читают еще классики философские. Здесь вдруг получается, что у нас нет вот этого молодого человека из Метрика, но он пишет, это незаконченное, это логика.
Чем он был недоволен? Непрерывностью? Сингулярностью?
Числом понятия вероятности.
Ну что ему не нравилось в понятии вероятности? Вот у него то, что приходит вероятность к популярным вещам, на самом деле, когда как бы читаешь книжку Паннейна, как раз такое впечатление, что он с этим делом справился, потому что он перевелся в квантовую механику на язык проекторов. И они как бы не сингулярные получаются. И проекторов не на плотности, а проекторов на распределении вероятности. То есть там этой функции нет, там есть ступенька. Ступенька это нормально, не сингулярная вещь, не все конечно. У него там семейство проекционных скрафтов не на определенное значение физической величины, а на диапазон. Физическая величина больше, там порог. Ничего сингулярного там у меня осталось. Я сейчас не могу понять, в чем причина.
Ну, тем не менее, когда он пишет, редукции нового пакета, у него все там все дискретно.
Ну, это другая история. Там неприятно, что все мгновенно и непонятно, где происходит. Но это невероятность. Это вот ему явно был непонятен сам процесс, что такое редукция. Он даже он Нейман был первый человек, который явно формулировал, что в квантовой механике есть два закона эволюции. Один закон эволюции дается равными Шрёдингера, а другой дается прикладным оператором. Вот он первый придет в гости.
современные, большая часть распределит просто склад какой-то.
Просто невозможно. Это те, кто думает, что они обошли без коррекционного склада, они не додумались до конца ответа, чем они занимаются. Потому что просто у них вот там где-то, значит, присутствует неявно. Вот, например, это самая концепция декодируется, которая основана на матрице работы с матрицей плотности. Интерпретация матрицы плотности основана на обратном проекционном постулате. Они просто закопали поглубже.
Зачем все надо было рассказывать, по идее, да? Там я насколько давно уже этим занимался, лет 10. Говорить слово.
У вас, кстати, по модальной интерпретации
интерпретация, ну, это меняется его форма. Ну, нужно как-то себя утвердить. Он пишет, обязательно становится свою интерпретацию квантовой механики. Ну, я же сам.
Ну, так она, если вы даже не слышал, гравитационный эссенциализм, целое же направление аналитическое.
Да, что вы там придумали особенно?
Я слово
Протокола. Что надо?
Есть, что природа является в том, что есть некие склонности, эти пропензии, да? Они не откуда возникают, а они где-то там на низшем уровне заложены. Не просто так случайно.
Мне как позитивисту совершенно непонятно, что это означает.
Но, тем не менее, пропенсия популярна стала, и вот есть книга Стапа «Квантовая теория сознания», там он пропенсию все использует. Ну, вы, наверное, ее читали, Стапа. На английском только есть, но это... Ну, Стапа очевидно.
У человека есть, да, склонность.
Ну, у человека много чего.
Разве есть?
Это не делаешь нормально.
Разве есть у тела, обладающего массой, склонность сохранять скорость, если у него действует тело?
Есть такой механизм, который можно подтвердить экспериментом.
Это можно анализировать.
Майкл Лекси пишет так: вот пусть система находится вне состояния оператора. Что можно сказать о величине этого оператора? Соответствующей физической величине.
Известно, что ничего.
Это инверсия.
Да.
Второй вопрос скрытых параметров. Можно сказать, но это неизвестно. Они остаются неизвестны. Третий вопрос, третий ответ на пропенсии. Причем он пишет очень крупно.
Это просто перевод, ну, не понимая, как бы с одного языка на другой. Я не понимаю на этом языке, но понимаю на другом. Но хотя, с другой стороны, как бы изобретение адекватного термина, оно во многом часто снимает проблему.
Понятно, что оно ее как бы не снимает, она просто, ну, дальше.
Оно позволяет не работать.
Да.
Ну, вот, значит, это не скрытые параметры.
Они как вот полуреальные, да, как недореальные.
Да, есть некие тенденции, есть какие-то. Знаешь, куда?
Ну, как у Макфарса, да, не знаю, кто даже
То есть, ну, я хочу сказать, что вообще любой духовный философ старается и папа, у него тоже свои интерпретации.
А он как раз квантовый.
Может быть, но не все.
Может, философская база, когда сказал, что быть мы квантовыми существами, была у нас квантовая логика.
А может быть,
это больше же его идеи, конечно.
Нет, вообще у него модель.
Ну, может быть, у него она была не одна. Вот он даже проводил линейки Евклидовой геометрии. Кто там говорил, мы были дурачки такие, думали, что Евклидовой геометрия от Бога дана. Ну, казалось, что это экспериментальная наука. Мы остались недостаточно развитыми, мы думали, что там логика от Бога дана. Логика тоже должна быть экспериментальной. Поэтому, говорят, вот квантовая логика, это логика альтернативы реальности.
У меня здесь еще это чуть-чуть любимый.
Это Андрей не работает. Он когда пишет, конвертирует.
Самое ничего нет. Мы все пишем на доске снова.
сейчас очень популярна информационная интерпретация. Ну, после Уиллера, да, и Фромбит, и всякими опытами, что тайминги.
Нет, ну вот в Хельсинки там не было.
То есть, даже такой том есть юбилей Уиллера, где очень многие физики развивают его идеи на как информацию рассматривать как некую основу.
Да, сейчас в архиве постоянно. Раз в месяц обязательно статья появляется вывод квантовой механики из информационных соображений. Что-то такое пишется, как бы интересно, но не всегда убедительно.
Ну, в любом случае, это актуальное направление.
Ну, это коррелирует немножко с тем, что я пытался сказать, что на самом деле за физикой может стоять какая-то не физика, а не могли, а что фундаментально не физическое. Информация. Но, правда, информация тоже неправильно, потому что квантовая информация – это не информация. Квантовая информация – то, что копируется квантовым состоянием, и это слышно лишено одного важнейшего свойства информации, настоящего. Копировать нельзя. Можно клонировать, то есть можно репортировать, а копировать нельзя. Обычная информация, обязательно свойство обычной информации, можно копировать неограниченное количество раз.
Как копировать информацию?
Да, да, да. Можно книжку издать любым числом тиражей и так далее. Квантовая информация существует в единственном экземпляре. Как дух человеческий.
Ну, потому что так, при любом копировании возникает изменение.
То, что возникает, есть теорема непланированного состояния, которая говорит, что можно состояние неизвестной заранее мыслительной динамики наблюдать за будущим. Поэтому, когда говорят, что стоит за сразу неправильно, потому что квантовая информационная не власти, не квантовая. Дело в том, что квантовая информация это совсем не информация. Вообще это другая вещь.
Убить, да, не убить, но это
Да, убит, вот состояние убита не есть информационное состояние.
А чтобы убить нельзя даже?
Если вам представлен убит, вы не можете с ним работать как с информацией. Вы не можете сделать себе еще один такой же механизм.
Передает информацию.
Телепортирует. Он в одном месте его убивает, а в другом месте пересоздает. Сделать два одинаковых убийств, в принципе, не может.
Нет, он сама передает.
Просто можно...
да, она убивает.
Да, можно передать, но нельзя копировать.
Ну, передать
Можно, да, информация вам просто передается.
Okay, let's just make general talk more officially. We have a round table and yeah, I'm sorry I had probably give some questions or topics to discuss, but yeah, very good, yeah. So I think the topic of this workshop is quite right. I have in mind that I have in this project is exactly, actually, that maybe moves closely related to your talk, where we have this big problem and actually, I think we are not satisfied. We are provoked by business to still give an answer. And actually, in my project, I also think that it's not a question of, how to say, only of explanation, theoretically explain why mathematics is effective, but it's also kind of, there is pragmatic aspect. Because if we just don't understand how it works, my guess is it's going to stop working. You see? And actually, there is no reason for that. Because, say, 19th century, there were some theories, right? And the kind of things you also, mentioned, like transcendentalism, so there were some stories how mathematics, works together with natural scientific experience. The problem is, and I think that's related to it, that actually in 20th century, this old answer, at least in their original form, didn't work, right? Mostly because mathematics changed so dramatically. You see? And I think that's also related to being the puzzle. Because this kind of philosophy of, popular philosophy of mathematics that you criticize, that was actually became mainstream already in the 20th century after people like Russell, etc., logical positivism, you see? So it's exactly a reflection of that picture that mathematics is something, constructed, really constructed, while experience something rigid in the sense that it just is, kind of imposed, and then we may wonder why one thing is another. Yes. So could be what I want to say. So I think actually we may also observe that a lot of mathematics which has been successfully used even in physics in the 20th century Actually, most of this mathematics was in Hertz earlier. Yeah. Maybe it's less to Hilbert spaces, but it's the thing, for example, remaining geometry. You see? For one day also asked why, Einstein took remaining geometry, because has been somehow developed like 60 years beforehand.
And someone took it.
Yeah, and one about it. But actually, it's very hard a special vision because if we look a little bit into Riemann, for Riemann it was physics to begin with.
In fact, Riemann said it explicitly.
Exactly.
Yeah.
So I think, of course, there is this explanatory stuff, but I think there is also a problem, how to say, that really modern mathematics actually is difficult to apply. And some cases like string theory rather something goes, if not absolutely wrong, then not as good as people would wish, you see. And so I think that such explanation may also somehow help, I don't know, say because it's philosophy, it's not physics, but may somehow help, to do science more successfully and somehow to apply mathematics better than we do so far. Something like this.
You mentioned some stories about that. I think it is problem of the applicability of mathematics.
Mm-hmm.
Go back as far as Plato, at least. Plato actually dealt with the issue, by believing that mathematics dealt with forms of a certain type, and that the real world was somehow a reflection of these forms. You find a way of making mathematics apply to reality, apply to ideal forms, which themselves apply to reality. You see this problem in Kant. Clearly, the critique of pure reason. It started with the question, in fact, of theoretical physics and mathematics, and he really got involved with the issue of how to make this make sense of this. But not only that, if you take Frege, for instance, Frege has a theory of applicability of mathematics. Frege says explicitly that physics is arithmetic. Arithmetic is a theory of a concept, and of course you can use the concept to deal with experience. And I think it's a noble problem, and it had many philosophical approaches. It's not a new thing. Definitely not a new thing. But you talked about the modern. In certain sense, I think that the experience somehow suggests the mathematical treatment. I think the matrix treatment of quantum theory is quite natural. I find it quite natural, in fact, because it's almost invited by experience. You have outcomes, an array of possible outcomes, and if you conduct experiments, you're going to see that they are actually certain probabilities, and how can you represent that? Well, the easiest way is a linear superposition. The easiest way is a linear superposition that invites a linear algebraic treatment. I find it is almost natural. Anyway.
Yes, please. I would like to say some words as remarks for Tom Jaro.
Oh, yeah, you missed that.
Generally, I agree with your opinion. Mathematics, of course, is not pure abstract structure. Mathematics is connected with human experience by filtering. But I would like to justify why I think cannot be right in our mind. It will be some other notion, but not the notion of classical set. There, in my opinion, the set is the simplest physical model. It's not abstract notion, but it is a physical model. The second, I go along provocative definition. Second is structure. The mathematics is studying on structure on set. Structure is also an abstract from the notion of properties and stable connection between things that exist in nature. Therefore, the notion of structure is also physical model. Very, very general, but physical model. It is not a pure abstract notion. And third component, the studying of structures on set is carried out in mathematics due perhaps of logical deduction. And I think that logical deduction is also physical model. It is abstraction of causal connections in real world. For example, if our world had not one time dimension, but two time dimensions, I think the usual notion of logical implication, linear logical implication as in mathematics, could not be right in human science. Therefore, it is exactly, and these three notions is due three main filters of human between reality and human mind.
I think I agree with you in general. Like that, you know this book by Edmund Husserl called Experience and Judgment. It's a fantastic book because it touches the issue that you have the logical level is anteceded by a pre-categorical, pre-logical level, which is not free of logical structure. And then, in some sense, in this book, you see how somehow logic connects to reality. And I think it's a nice expression of this filter that you mentioned. It's interesting. Another thing that you mentioned that I like is you mentioned Sept. I don't know if you know this journal called the New Yearbook of Phenomenology and Phenomenological Research. This book is a book published.
Alexander the physicist actually,
yeah.
So,
It is
I also not quantum physicist and cosmic relations. Astrophysicist.
Anyway, this journal is the last issue of this journal. There is a paper of mine entitled "A Phenomenological Approach to Sept Theory," in which I do precisely what you said. I show that, well, because the mathematical Sept theory deals with things like infinite Sept and not infinite Sept.
This is the property of the model.
Yes,
but the model has the root in real physics.
That's what I say. Because in this paper, I show how you can make this abstract Sept theory to sit on a physical theory, which I call physical Sept. And then I'm going to send you this paper because this is precisely what you said. I'm following the lead of Husserl here to all this abstracted formation. I am in fact sitting on very almost basic experience, and there is a gradation of intentionality involved in viewing this thing. I agree with you completely.
Yeah, guys, but maybe I believe when I finish my mind, it's very short. Therefore, the mathematics that we have actually is classical mathematics. And other mathematics may exist. The question is, why classical mathematics can describe quantum world? I think the reason classical interface. And our classical mathematics correlates with classical interface. And we know nothing about quantum world itself.
Yeah, but may I just be critical about what you're saying? Because, look, first thing, what you described is a kind of, if we are talking about, say, more to physics side, later I'm going to say philosophy side, but more to like mathematics and physics side, you describe kind of desiderata, right? Something we would like to, which, if what you say would be correct, right, we would indeed have kind of nice theory of, not maybe theory of everything, but kind of very nice theory which would somehow naturally, very naturally combine logic and mathematics and physics and experience, and it would be transparent how it works together, so it would be perfect world. But the thing is that the world is just, it simply says there are evidences that it doesn't work. I mean, as any empirical evidence, it's not like final evidence, right? We can only say that there were efforts in exactly that direction, some of which I mentioned in my paper, right? At least starting with Supers and other people, just exactly push that project. You see, somehow translate physics into the language of set theory, and there was of course this underlying metaphysics we may say, or if you don't like the word metaphysics, just call it motivation, however, just as you say, that it's just kind of simple notion of thing, and it's a basic, and so forth, so forth. So why physics wouldn't work that way? But it simply does not. I mean, as far as we are now, perhaps we may change everything, it would come, but it simply doesn't. And I think, and one reason why, yes, in a sense, it's simplistic. I mean, in a sense, you just somehow derive your primitive notions from, I don't know, metaphysics, or perhaps it could be not metaphysics, but phenomenology, and somehow you say, let us be physical, right? No, in reality, it's a bit more complicated, right? Because you really borrow already notion of set somehow from mathematics, it's still there, and so you can apply it to physics, it would be, but, and so you are trying to justify it, right? With some additional, phenomenological arguments or, metaphysical arguments. But I think simply there is no evidence that it somehow combined with what we today consider our best science. And for that reason, I think there is really good reason to look a little bit back, right? And also look at, successful science of the past. I totally agree that what is successful, of course, would be questions, I think, for you, for others. Yes. Yeah. And so we may look how it was there, right? Of course, it's not a question just to debate, because we different mathematics and different physics, and there is all this problem of scale and how we make experiments that we can perceive directly electrons and stuff like this, the symbolic representation. But anyway, I think this is where we may have some, some hints how it may work. And these hints actually suggest, I think, something different. And not at all just taking this, this project to make physics or use logic, classical logic plus that theory kind of basis more resembles what physics used in the 16th century, kind of scholastic thing where they also try to make physics, first of all, logical based, not on mathematics, but on logical, first of all. That was like the Parisian physics of the 16th century, for example, you see. And now we say that Galileo, these people still made a progress, so I would think that could be, I would say, better maybe. Of course, we may use everything, we don't know the future, but at least I think we should be very cautious. And this is actually part of this new Kantian attitude, that one may be something want and imagine and make theory how it could be very nice, but a different thing to make it in practice. And as also, for example, right, we are not in a position just to remake the whole thing. So we should take seriously what is going on it doesn't mean uncritically, but seriously what's going on really in science, right? So
Yeah, I don't see any contradiction because the only thing that we as science is that no matter how elaborate your mathematical is, it essentially takes on concepts that are related to immediate experiences somehow. You know, it's related to immediate experience. Of course, you build on top of that. You build, and you create
but I can well imagine, I did read your paper, but I was like it, but I more or less, may imagine how you may really justify this idea of using, I don't know, sets and relation and group-like structure as kind of foundation for exponential science. So I imagine how you may relate it to kind of simple human experience and stuff, but it's much what I cannot really see, how you can really effectively connect with scientific theory, and not just in principle, but somehow.
Because almost all scientific theory of today uses classical mathematics.
Yeah, but exactly that's the point. It's not, this is not enough. If you just stop at that point, right, you say, that uses classical mathematics, we know how to formalize classical mathematics in no, I think it's just not enough, because it just gives you some, some very, very speculative argument, how in principle you may, going down your physics to sets or something, but it does not give you anything like, set theoretic foundation for physics.
Can you give us a specific example of a physical theory which dismisses mathematics that's not built on set theory?
But
Sorry. Physics depends on set theory through the number theory that is based on set theory.
Okay. Yes. No, just it's what I tried to say in the beginning of my talk yesterday. This depends in this context. It's too weak. It means almost nothing. There is kind of translation of, say, mathematics used by physicists into set theory. But that's kind of trivial in the sense that when you say translation, right, normally you should require that something is preserved. You should somehow give a criteria that this translation does not, confuse your term, doesn't make something wrong. And this is really somehow fair presentation and for set theory there is no feasible translation already. That's I stress, right? So these things are unfeasible. Unfeasible not only on computer, but even, very, very quick to count big numbers. So it's something absolutely existing only as very abstract mathematical object itself.
But even you can make a point for a completely sort of foundation. I think it doesn't change the philosophical problem of future. Oh my God, if you consider theory for another type of theory, there is no.
You see, if you are so liberal about your notion of translation, I can really translate almost any theory to any theory. You see? So I can translate all physics to some, I don't know, very simplistic metaphysics. And say this simplistic metaphysics is the base of everything. Physics say, okay. So it would not be, first it would not be scientific claim, and it would not be good philosophical claim, because it would, for physicists' viewpoint, it would just mean you kind of associate these physical theories kind of waste talk of something of which physicists don't see any purpose. You see? And actually, I'd like to say that problem is not only on this interface physics and mathematics, but also on the interface of kind of everyday, mainstream mathematics, or what mathematicians are really doing, and say some logicians, philosophers. As I said yesterday, nobody in mathematics today use this existing set theoretic formalization. Set theory is used in very special informal manner. So, And in my view, that is actually, so my strategy is different. Of course, it's good to have different strategies, but I would say that exactly that kind of thinking about mathematics, which puts around set theory and this connected logical talk and sometimes metaphysical talk as the official foundation of mathematics, which by the way many important mathematicians absolutely deny 20 years ago, right? Yeah, but I think that makes kind of how to say problem. That may be gap between physics and mathematics, and which I hope to how to say to fill exactly. But think about new types of foundations like this molecular theory, in particular, not only because, but in particular because it may how to say restore this kind of better relationship with physics.
I hope you're lucky. Just see for the result.
Yeah,
Okay, but I think that your new foundations of mathematics generally equivalent, but by Bourbaki construction, but best suitable for computer realization. Do I understand correctly?
it's just one of these things, you know. Just one of these things. That indeed, no, I mean, you know what, yes, then people started, you know, this semantic test theory, logic, in the algebra in the beginning of the 20th century was a huge development of quantum logic. But if you look today, just so many things that developed there, they developed, I mean, theoretically. But today, because of computer technology, we are in a position to realize that this is part of what these people just, you know, speculated actually about, but speculated mathematically, but you can speculate. Today we are in position to make something of this dream too. But as always happens, you know, when it comes to practice, you need, or you have more things to reflect on. You see? So it's not like you cannot just stick to the same old picture, which is, in a sense, completely idealistic. It's more actually interesting things coming. So one thing indeed that of course, it's obvious, like you cannot do science without computer, and it's not even done. Right? Imagine kind of calculation made for LHC experiment was already there are calculations apart. Right? So it's one thing that you can make it computable. But I think there is more than that because at least in this homotopic I try to suggest, right? It kind of suggests this idea that the game may form something like common foundations for physics and mathematics, but not which would not base in some other external theory, right? Like phenomenology or something, and would take some concepts which actually how to say align to what physicists and mathematics know, at least what physicists are doing, you know. Most physicists never heard about, you know, semantic test. Just not part of their, how to say, education and their practice. Huh? So what? No, I mean, you want to say that.
The point is that maybe physicists do not really know what they're doing. They must be told what they're doing.
Yeah, of course, you have a lot of strategies as a philosopher, logician, whoever, somehow to justify your niche, your place in that saying, okay. And that's actually what happens in this business and axiomatization today, right? Because some people still go for that, physicists are not interested, and these people say, okay, we are not trying to, how to say, to steal some money or, you know, from physicists, we just doing our small business or logical analysis or something like this. And physicists just are not interested, you know. But when I compare that with what we heard in the Renaissance talk also, and we heard in your talk, that people like Paul Neumann, they really tried it, you know, to do really projects, not just imagine how physics could be if the concept of Sept would start to be physical. You know, we can imagine that and find philosophical, but it's absolutely different thing to make it practical, and which I don't know, belongs to philosophy or belongs to physics, but it's just more interesting somehow. Of course, you may speculate. I don't deny that. I don't say that we should not speculate, but I just say we should also try something and be, as philosophers, and be attentive to what's really going on in physics, which of our ideas work there and which apparently don't. Of course, we may try to do them, we should, okay? But if for 100 years nothing happens of this report, I think it's really reason to change a bit our ideas.
Do you know that I have a book here with the title is Doing Physics with Quaternions. You know this?
I came across the title again, but it's really...
It's like Douglas Switzer.
Yeah.
It's funny because, you know, this is an example that you can choose more or less the foundation you like better. This guy decided that he was going to choose the quaternion. And then he does develop it all in this book. He does classical mechanics, special relativity, electromagnetism, quantum mechanics, and gravity. I mean, pretty much all of physics, only using quaternions. Which is funny because it shows, I think it shows something interesting, that provided that your foundation has the necessary structure, you can choose anyone. You can choose anyone. It's just a matter of which one you feel better with.
So my take on this is that you cannot up to a certain point. You see, of course, you can do just a lot of mathematics and also mathematical physics as people did. I don't know in the beginning of the 19th century in classical mechanics. So they didn't care about foundation, right? But they do very, very good, successful mathematics and mathematical physics. But I think that just works until a certain point, but really you need to, to systematize. You cannot just continue and say, I don't care, I take this foundation, that. That, by the way, the most popular attitude among, working mathematicians. They say we don't just simply don't care. But I think even in physics and mathematics, there are moments. For physics, I know that, but for mathematics, I may say. For example, Vladimir Voivodov, that I mentioned, he was not initially a logician. So that work just came from his work in the Marquis theory, which is really top-age research in mathematics, and he just discovered he cannot continue the future. He can't remain arrogant to foundation. For example, Grothendieck was, right? He was never, that was already other people like Clavier who take top-stage foundation. Grothendieck just did it. And when people really pressed him to talk about foundation, he did something like this Grothendieck process, which is not very complicated and interesting. So he remained arrogant. But I think that position is simply, if it would be consistent and stable, we would never talk about foundation at all, I think. Right? And,
No, just I wanted to comment about quaternions because for me, using quaternion rather than groups, because they are more or less the same thing, is exactly like if you make philosophy in French or in German, or it's the same thing more or less.
Yeah, that's
but
what I got.
Maybe I would like to comment about your talk this morning and the three levels. I was trying to compare that to my own vision of that, and finally, I like the idea, but I was wondering if it's possible to formalize it and to make it agree with what I think. And in fact, I think I do not agree completely. I agree more or less with the division in three levels, but maybe we need more or less. I don't know exactly. But my first comment is about that level that you call perceptual level. And I understand, I think, what you mean, but I think this is not part of the way physics is progressing, because for me, physics goes against perception, and I can give examples, many examples. For instance, Newtonian physics, because your perception, they said to you that you have horizontal directions and vertical directions, which are very different because you object for following the vertical direction. And the basis of Newtonian physics is that you have isotropic space, so you're going against perception. If you take relativity, your perception says to you that you have space and time. And precisely the Einsteinian physics is the rejection of space and time. So I would like to replace the perceptual layer, perceptual nature, by conceptual nature maybe, and say that this is the level where you have theories. And if you take different theories like Newtonian or Einsteinian or quantum physics, the choice of a theory is what I call the choice of ontology, some kind of restricted ontology. So you have the first layer, which is real nature, independent nature with some kind of independent reality. And the second layer is trying to approach that by defining some practical ontology, which means choosing what are the objects of your theory. And if you are Newton, you will say the objects are space, time, and particles. If you are Einstein, you will say this is space, time, and particles. If you are in quantum physics, you will say this is space and time and, for instance, wave functions. So each time you have a theory, you have an ontology, which means that you define what are the physical objects according to that view that you have. And of course, all these ontologies are contradictory to each other. And this is one big problem of physics, how to reconcile, for instance, the contradictory ontology of quantum physics and Einsteinian physics. And in the 19th century, it was a problem how to reconcile the ontology about electromagnetism and Newtonian kinematics. And this was the origin of special relativity by Einstein. So maybe you have the second layer that I call conceptual, which is exactly going against perception, against common sense, against what you see. And then you have a third level, which is the mathematization of that. But even that, when you have a given theory, for instance, a Newtonian theory or Einsteinian theory, you have many different formulations. So the correspondence between the second and the third theory is not one-to-one, because, for instance, if you take my presentation of yesterday, what I've tried to show is that if you take, for instance, general relativity, you may have 5 or 6 or maybe more different ways to express it, which involve different mathematics. And of course, when you have these mathematical models of a theory, you have some kind of relations between them, because this is the same theory, and these relations are isomorphism or functors or dualities or something like that. And you can usually express all these relations in a functorial way, and this is one of the force of the categorical approach. So I don't know if you agree more or less.
I agree. I agree more or less.
Yeah.
Because you are in the same direction I am, that
Yes.
there is a distance between nature out there and nature
Yes.
out there. The opposite in this.
I think everybody would agree on that.
Yes. The point is how to which step in the way.
Yes.
Well, you're right. You're right. What you call conceptual nature, I see already as part of that physical nature, because physical nature involves conceptualization and mathematization, and sometimes reconceptualization of perception, which you call going against perception. I say reconceptualization of perception, because even when our conceptualizations of perception go against perception, in the end they have to make sense of perception. Of course, I experience spaces has non-isotropic, for instance, right?
Mm-hmm.
Non-isotropic. In my physical theory, this space is isotropic. But then I have to explain why I experience it as non-isotropic. Then I give a reason. Well, I have this favorite direction because there is a a force field here.
I do that by introducing a new concept,
Yes.
gravitation.
Yes, gravitation, that's it. But then, in the end, our perception has to make sense.
Of course.
It has to make sense. And it has to make sense within the theory. And when this going against the perception is maybe a first step, then you have to make sense of that. You know? But in general, I agree with you.
I'm not sure that the word perception is okay. If you take, for instance, the Higgs boson, and now the Higgs boson is part of the ontology of particle physics. But what is the link between the Higgs boson and our perception?
Oh,
Yeah, but there is a link. I mean,
Sorry?
no, I think there is an important link. It's not something unexistent or strange. Because I
It's
think
not so long.
What do you mean?
however long, but I mean, still is absolutely fundamental. That's why I have to feel, maybe explain.
Okay, I
because
don't-
yeah, I think it's very important. I think we right discriminate between what is speculation and what is physical.
I agree, but it has nothing to do with our perception. It's a very complicated reconstruction.
So what?
Yeah,
but we call it complicated, but I mean, as far as I understand, maybe wrong in your saying, but just the concept of experience, which we agree is fundamental because it allows us to discriminate what is speculation and what is physics, right? And but this concept of experience naturally involves perception. There is no experience without perception.
Of course, this involves some kind of perception, but I agree that, in fact, you are going from first to second to third level and back. And perception is involved in the back motion, not in the construction of theories. Construction of theories goes in my sense again perception. And this is another way to say that there is no experiment or observation without a theory behind.
Of course not. In the end, the only thing you perceive in certain realms of science is just a pointer pointing into a number. That's your perception.
But that's
The
what
rest is only from what sense you make of that, and then you need a theory.
You don't even need a pointer. The pointer can be digitalized and give you a number.
Yes,
I agree that you have to read the number at some moment, but this is the only
interesting question also raised by Alexander around the Alexander just told me, and I think that's the kind of thinking we really find in Bohr, for example, so was our factor for 20th century. You say, okay, they are macroscopic creatures, right? And what we want to study is quantum mechanics and microscope. So we cannot have anything like direct experience of the microscopic events. So what we can do is somehow represent them, translate them into our microscopic, I don't know, perception things and whatever. But I think it could be, actually that has kind of an analogy, but I think pretty much close analogy in mathematics, in pure mathematics. Even because it was evident also that, for example, you cannot imagine non-Euclidean geometry, right? So what you should do some kind of abstract theory and then look for a kind of usual Euclidean model. Even there is not, strictly speaking, but you may like Petrani, pseudosphere, that kind of thing. And so I think it's questionable. So I don't think we should just take this assumption. It sounds somehow reasonable, but I think it's very questionable. Already, if you look for practice of 19th century, for example, Lobachevsky, he did imagine, hyperbolic space. He actually found the non-standard model of Euclidean plane in hyperbolic space. That's how it works. Not the other way around. And coming to physics, actually, if we talk about this thing, why we should think that our, say, usual classical modes of perception, everything that makes basis of classical physics, just could not be developed. Why we cannot, I don't know, since our cognitive apparatus is somehow also, I don't know, quantum device, So we have to make just develop some, we develop our techniques, we develop our concepts, we develop our experimental setup. Why we can also develop our brain and our something, right?
But we do.
Yeah, and in mathematics today, I think it's also right kind of big change, a different style, I would say, parameter, but a different style. That, in the beginning of 20th century, just people try to be more formal, just avoid making images something. But today, this is not the case. Just people in very modern concepts, just people try to use more and more, pictures and kind of conceptual geometry, but in a new way, not in the same way that, like you. So I think that's really, how to say, questionable. That is, by the way, behind Bohr's philosophy. That's behind the dispute between Einstein and Bohr. Right? Because that was Bohr's philosophy. That somehow we cannot have anything like realistic model of quantum, system, right? Exactly because we can only present it as kind of classical images, which would not combine together in one. But I think that I would call not perhaps ontological, but kind of epistemological dogma, which I don't see really reasons to stick to. So I think we should just really try other possibilities also of imagination, of intuition, and the acts of perception. It goes again.
How natural selection,
Huh?
how natural selection can develop so possibility for us it is absolutely unclear. How we can understand abstract geometry, geometries, and so.
No, it is clear, absolutely honestly. But I think today every mathematician does something like hyperbolic space. Now, of course, it's a matter of experience. It just we should abandon this vision that is somehow wired in our brains, right? And just take it develop with education, with practice.
I read the book, I can't remember the author of the book. He makes the point that we actually perceive space hyperbolically. And he made a very interesting point, that our perception is actually hyperbolic, and we somehow rationalize it as if it were.
So my assumption is following discussion is that it's really something educated. It's nothing like really wired. Why one reason for leaving geometry, why it was so, it actually seems to be rather good, except pure mathematical and logical reason. There is actually one which connects, because only Euclidean geometry makes scale. So making some good model of, I don't know, pyramid, you can only make it. Why? This one reason.
Well, as Mark said, the experience clearly indicates that space is finite, right?
The space is
Finite.
finite.
Finite. Experience, our perceptive experience indicates that space.
I'm not so sure about
I think it's the only way we think that our space is infinite because we conceptualize it as such. Because we never, from the testimony of our perception, we could very well be inside a ball, right?
But infinity is not something perceptible by definition.
Oh, of course not. That's my point. That's my point.
But it does not prove that.
The infinity perceptible is a process without feeling.
Yes, it is on the
Not as done, but
what do we know? What do we know is that we extend. You can extend our perception, but this is not infinite.
Yes, but it is not finite either. So
Yeah.
it depends what you mean by infinite. Because if you mean infinite is not finite, so it is infinite. But if you mean infinite like the big infinity, which are well defined in mathematics, of course, this is not in perception. But we don't perceive the space as finite.
No, we don't perceive it as having boundaries.
Sorry?
We don't perceive the space as having boundaries.
Well, this is a different question.
So,
Because
there is no boundary, but this doesn't mean that we cannot.
So I guess the right concept is compact, like topological, right? I would say so. But I would say we ignore it, receive it as compact. We kind of don't know. It could be compact, it could be not.
This has been a long debate.
Yeah, well.
What could I say? Yeah, I'd like the sort of Mark. I am sure that we can say about nothing experience without, as Mark called, ontology of theory. I'm sure because any perception without previous concept, what we want to perceive, how we try to combine, in what language we could explain myself, what do we perceive. I think it's impossible, and we know that the same phenomena we can describe very different theories with absolutely contradicted ontology. Not only in classical mechanics, Newtonian mechanics, rational principles, field theory. In quantum mechanics, I said yesterday about three formalisms without similar mathematical results, but they based on absolutely different ontology. But the question is why? Why this very similar resultative formalism based on such a different ontology? But I want to say about another. When I read the aspect of this workshop about unreasonable effectiveness of mathematics, I don't think that it was just provocation. I was naive and believed that it's a real question. And in fact, many of us don't try to answer the question, but we try to reject this question. There is this question illegal, and so it's a good decision. Maybe I'm wrong. I think this Wigner's question consists of two parts. What's the reason of consistency between physical theories and mathematics? Of course, we can say that we perceive and try to explain our experience in mathematics that we created before this perception, for this explanation. Okay, but the second part of problem is what is the source of our mathematics, our way of thinking using mathematical concepts, using different logic. Why, if we can order our thoughts, our concepts, what is the reason this ability? Why we have such ability to order our concepts? It's okay. There is several answers. For example, it was the result of evolution, perhaps accidental result. Or the second answer is just experience. The source of our ability to order our notions is just
сейчас не посидишь, может, тогда это самое,
The third answer maybe there is some external source of order. And I'd like to say about this reason. Why they have such ability to create mathematical concepts? Why? And my idea is we have to try to use some mathematical concepts to have some references outside our mind. Yeah, it's just my idea, and I like to talk about it, but most of physicists say it's not question, it's too metaphysical question, and not say about physics. Yeah. This is my problem.
When you look at the history of mathematics, right, the first notion were obviously very related to our experience of reality. Right? Like counting, for example.
Triangle.
You know, counting. Let's say counting. No, counting.
Let's
Very basic.
circle
Counting. Counting. It was already something that 3,000 years before Christ that people are already doing. You know? And even before, maybe. And so when you come to that first, there was no theory of numbers, and there were no numbers. But there was counting. Counting was an activity. There was no concept of pure number, of mathematical number. Counting was an activity. It's something that you did in order to tally things, in order to keep track of things. You have to keep track of things. For instance, you have to keep track in a religious ceremony with the first to talk and with the second to talk, right? You have to make order, to put order in life. And you have to keep track of things. This naturally conducted to notions of cardinal number and ordinal number. Of course, they were not numbers. If you look at all the number system, you see that they are very connected to what they're being numbered. Now, to say Jew duck, I just say Jew stars, sometimes you have to use different words because they're not the same thing.
But today we come back to this idea using typing. That was clever, actually.
Good, so you're going that way. But at certain point, someone might have realized that two dots and two stars do have something in common, right? And then this is a higher level of abstraction from reality. At this level, we do come up with abstract numbers, pure numbers, but not the theory of numbers yet. Only with time, we sort of looked at these entities as objects of interest and tried to develop theories about them. And it's a gradual thing. It's a gradual thing. I think history of mathematics shows us how gradual mathematics is and how concepts somehow are built one on top of the other. It's a complication, it's a scale. Of course, if you look at the present day mathematics, with extremely abstract concepts, functional spaces and studying metrics in infinite dimensional space. Of course, those things are highly abstract and far from experience. But if you look at their history, their history do show a certain gradation and a certain sophistication. Like, for instance, Lakatos, when he said that, you cannot do philosophy of mathematics without looking at the history of mathematics in order to get the right perspective. So in the end, I think that all boils down to we confronted with
Right, but make I just continue. I think what you just said, I completely agree. But I would make, how say, add something. I don't know if you agree or not. That I think Husserl, no, I don't know well Husserl, but my picture, maybe you correct me, somehow believes that how we know the world, there is kind of primordial, I don't know, situation or something, right? Which has nothing to do with science, with physics, but with kind of deep, this, you know, how do you call it? But I frankly, that part I wouldn't buy, right? And I would say, I agree completely what you just said, but I would say it's kind of continuing process. It's not just kind of set up once and for all, and it continues. And moreover, we kind of strange features, or maybe we just observe ourselves in too short a period, but it actually changes rather dramatically through what we call history, right? But then, you know, my picture is what mathematics really does. I agree, it's kind of rooted, however, in what you just explained, right? But then, very, very fastly, mathematics completely abandons this sphere on that experience on which is somehow, in which it's rooted. Use that one, right? By the way, a role is played in this process by symbolic notation, because even very simple and primitive symbolic notation immediately allows you for numbers bigger than number of variants. Yeah, very, very easy. So it's natural. But, and then there is kind of predictive power. So we, put it kind of simplistic way. For example, we never experienced in our practice number bigger than, say, 1,000, but we do know how manipulate with them symbolically, and so we extend our experience. We have practically some experience with the number of objects like millions, and it does work. So say it's a miracle. Look.
Just to complete that, and sometimes by imagining there are infinite numbers, I make the theory simpler.
Right. Wait. Exactly, because I was going to say that, in my view, infinite is kind of just sign of it's a huge simplification. It's actually simple than big. That's I mean. Infinite. Yeah, but what I say, so it works. But my guess is, and perhaps partly observation, that it works until a certain point, that it may break. You see? It's with numbers we don't actually, it was Kolmogorov's idea that big numbers may different arithmetics, like with big distances you have different geometry. You see?
It's like Cantor. When Cantor arrived at the notion of transfinite number, in fact he was working in Fourier theory.
I know.
And then he had this notion that, of a very concrete notion and an iteration, and we realized that you can iterate beyond the infinite.
Yeah, but if you compare, perhaps it's going to. I know you know his rejected paper, which was published recently by what was his name, Guinness, who died a couple of months ago, British historians of mathematics. He actually. Yeah. Because their counter speculated that, for example, with the different cardinalities, you may distinguish between animated matter and not animated, that kind of thing. So he thought about physical applications, actually.
Believe that infinite set of
that non-countable set would be living matter.
Exists.
Yes. He speculated that.
All the things that exist in God's mind.
Yeah. So he did want. No, may I just finish? Sorry. That he did want, as Alexander also said, to make set theory somehow foundation of physics. But we may say he was not successful, and he still much more took from philosophy than mathematics. Yeah, much more than and I think that's one of reasons why it didn't. So we may compare his case with Riemann's, for example, right? Because Riemann also made a brand new mathematical concept
also based, by the way, on experience through Gauss for the measuring. Also speculating already about possible physical application, and bam, and it worked out. So we may actually look, Riemann, Einstein as kind of participants of the same project. So Einstein accomplished what Riemann began. Of course, Einstein had to have new ideas. I don't say that the whole.
Riemann couldn't come up with a generalized notion of space without the work of
Gauss, of course.
And it is in geometry. They needed Gauss, and Gauss needed calculus, and calculus needed itself. And those things build up one over the other.
No, of course. But what my point is that if we specifically take case of Cantor and set theory, and so everything suggests that that's a failure. This Riemann is a great success. Riemann, Einstein, as you mentioned, Gauss, and back, to Euclid. Yeah, but that is a great success, right? But Cantor is apparently failure, and I think at least we should somehow conceive this possibility, not just saying that. So everything suggests it's a failure, and of course it's empirical claim, right? So it's not something I may claim for some, logical ground. It's empirical claim. Maybe someone say, okay, we still don't know how to do really right set theory. Some people think about that, right? That just, what is not Scheller, but this guy who is the most prominent in Wooden. Wooden. So his idea is that just all this Zermelo-Fraenkel just completely dead end in set theory. But Simon Hobbes would be really good set theory. Perhaps. But we should also, I think, there are signs that exactly because he somehow decided to make more weight, as you say, to theology and metaphysics than physics, that it just didn't work.
Their theories, their concepts simpler and simpler. What is the source of this intention to simplify? It's an intrinsic intention in our mind to economy of mind, or there's some economy of nature, mystical. What do you think about it?
You seem to be quite fond of going to the museum.
It doesn't matter. I want to hear your opinion.
It's proper to science because if you look at the system, you can describe it completely by describing absolutely all details. And this is not very interesting. This is what is called big data, maybe. And then you can have an economy, and you can say, for instance, it's a sphere. So instead of describing the position of all points, you say sphere. And it's saving a lot of description of time and place of description. And if you also want to describe and in a compact way the time evolution, you need to know the laws of nature. No, but how the system evolves according to which law. And in fact, for instance, it is sufficient to describe the initial state, and then you get all the evolution because you have a law. So this is just how to describe the things. And when you try to do that, you realize that it is possible to economize, to get simpler and simpler by using laws. And for me, it's a basic step that physics allows to accomplish. And it's true that in physics this is a criterion for a theory. The simpler is a theory, the nicer it is considered. And for instance, if you compare two quite similar theories, which are Newtonian theory and special relativity, they describe more or less the same circumstances. I mean Newtonian kinematics. And they have similar structures because you have principle of inertia, principle of relativity, composition of velocities, things like that. And what you see is if you you want to express, for instance, the inertia principle in the Newtonian context, it is much more complicated than the same principle in the Einsteinian context. You need one sentence instead of three sentences, for instance. If you want to express composition of vectors, of velocities, including the light, it is quite complicated in the Newtonian context. In the Einsteinian context, it's just a rotation of space-time. It cannot be simpler. So I think really that scientific progress goes in the direction of simplicity. Why? Sometimes, why? Why? Because this is our weakness, I would say.
Yeah.
Because this goes also in the sense of efficiency. For instance, if you want to predict what will be the weather tomorrow, what you can say is just look at all the data and trying to find analogies and things like that. But this would be a huge work, which is in fact impossible even using computers. If you know some physical law of, for instance, hydrodynamics and so on, so you can have models, and these models are very economical. And economical is the same thing as efficient. So this is a possible explanation, I think.
Well, if I may add something, take the notion of symmetry, for instance.
Yeah.
Symmetry has a vital importance for us. It is vital, you know. We can even give a biological explanation why symmetry is so vital to us. And then naturally, we find symmetry as quite a compelling notion. And more, we tend to adjust our aesthetic criteria. Aesthetic criteria by symmetry. We find symmetry more beautiful than non-symmetry. We objectively find symmetry more beautiful. And then our theory, the role of symmetry is essential in our field of theory, right? It plays an immense role. And also the same thing, I think, simplicity. And if you see all the way through, you see that simplicity also is a vital concept for us. Our life is independent, you know? And so there is no surprise that we do make simplicity a very important parameter of analysis of our theory, because it is an important parameter in our life.
I think it's logical circle.
No, it's not. It's not. But understand that we can understand why certain concepts like simplicity, symmetry, or elegance, or economy of means are important for us. You can make it, and these are science. Then there is absolutely no surprise that we make it important in science as well. You know, why shouldn't be that? Of course, we want simpler theories because we are limited people. We are very limited people. No, we are not very smart. We are not very smart. We need simplicity in order to make it, to get things.
To survive.
Yes, to survive, to understand it, our criteria of understanding. Understanding, basically, is giving the same name to different things, right? To make them, in a way, controllable or similar, things that I can understand.
Kind of weak.
You want something more transcendental, right?
I have read conception. He explained the circle or direct line from perfection. But, of course, for Leibniz, the first source of world's perfection is perfection of God. Yeah. But he had a theory how we could transfer God's perfection to a physical
Yeah. So thank you very much indeed for everybody. It was nice, very nice.
Thank you, Andrei.
Thank
you, Andrei.
Yeah, so I think tonight we may go together for dinner. So everybody of course is join. Everybody pays for himself. Unfortunately, not everybody. So, but on the other hand, it allows not discriminating.
So we meet at Institute?
Eh?
We meet here at Institute?
No, actually, if we're thinking about concert, there is a Scriabin concert, I think,
where?
With Klipnyov, guy.
Where is that?
In,
He's great.
He's
Where is that?
About 15 minutes walking from here.
At what time?
In 19. So I should check if there are tickets. Could be.
We could meet here at 6.
But I would join you for concert. I would like to.
You will not? You will not come to concert?
Yes. Yes, I do. And c'est à côté de ce resto où on était hier. Donc après on peut aller à resto.
See if there are available.
Yeah. Maybe I can even buy through internet.
Yeah, if you can buy, we give you in cash. I go to the bathroom, I can buy.
Yes, there are. Oh là 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 là. Что? Ну вот смотри, мы хотим в консерваторию пойти, я думаю, что мы попадем. Пошли тоже. Вот. Да, и там же рядом поужинаем. Вы сейчас хотите сюда? Ну в 7 там начинаем. Все уже, все закончилось. Спасибо. Сейчас только мой переходник.
Donc on se retrouve, j'ai pas entendu.
Attends, mais on va ensemble? Да? О, нет, спасибо. Attends, mais on va ensemble là, conservatoire, et après le concert, on va manger.
Oui, mais c'est à 6h.
Voilà.
On se retrouve vers 6h ici.
D'accord.
6h30, 6h?
Attends, mais il faut vérifier avec les billets quand même.
Je regarde.
Peut-être on peut acheter comme ça, je sais pas si c'est... Aujourd'hui c'est les 22, oui.
Aujourd'hui c'est mardi.
Papa, pourquoi je n'arrive pas...
Est-ce qu'il y a
Je comprends pas parce que j'essaie d'acheter par internet.
Et ça ne marche pas?
Peut-être c'est fini, tu vois.
Et il est vraiment merveilleux. Je l'ai vu à São Paulo. Hein. Il est quelque chose d'exceptionnel.
Mais il est vraiment dégueulasse, quoi. Le soutien Poutine, tout ça. Et franchement, musique, oui, c'est pas mon préféré. Non, tu sais, les Russes, Berezovski, tu connais bien?
Oui, Berezovski.
Et le deuxième, qui joue Chopin. Le russe aussi.
Ah oui, il y en a beaucoup. Hein.
Mais, ouais. Attends, j'essaie.
Oui,
c'est le 1er octobre déjà.
Ah oui, ça
c'est peut-être il n'y a plus. Mais peut-être s'il ferme Internet, bon, je sais appeler.
Oui, appelle. Et des ventes, il y a un ticket pour aujourd'hui, hein, on peut y aller.
Oui, je crois que sur Internet, ils vendent en avance.
Ah oui, je sais, ouais. Mais quelquefois, ça ne marche pas tellement bien.
Алло, здравствуйте, а я хотел бы вот узнать насчет билетов в Большой зал консерватории сегодня. Там забронировать, если можно. Алло? Да, на сегодня. Подождите, а Плетнев это не сегодня разве? А, он в зале Чайковского. Ну тогда в зал Чайковского. А, точно, вот я Скажите, да.
You know how much I paid for last show tomorrow? 15,000.
Да? Ну давайте подумаем. Не, ну выставить вообще не проблема. Спасибо, Саша, огромное. Там два всего на связи. Спасибо. Мне нужно, и мне надо. Всего доброго.
Thank you very much. Thank you very much. I wouldn't mind if they do about thing is Tuesday.
Okay, but that should be nice. No, I just don't want to pay because I know that I may have that or even better for. But Pietro, we should go there together. Maybe it'll be cheaper tickets. That's what she said.
At what time?
It begins at 7. Now it's 5. So 2 hours.
Yeah. Well, it's time for me to go to hotel and change. And where is that? We can meet at say 6:30 in this place. Where is it?
No, I thought she said this.
If there is no ticket, we can just go for dinner.
No, look, let us meet in an hour. It's too short.
No,
At 6.
At 6.
At 6 downstairs. Here.
Downstairs. Okay.
Not in the road.
Okay, 6 downstairs. Okay. I see you later. 6 downstairs?
Yes, yes. And у вас видели такие, что мы можем попозже. Mais vous, vous avez. Non, c'est
5 minutes.
C'est 70 ou 80. Mais c'est le même comme on a dit, tu peux faire. Je vais à Madrid qui font tout un voyage pour rien. Si je fais un livre, je veux ça. En fait, je peux expliquer comment, je sais comment faire. Pour voir si de genre $10-15, font les meilleures places. C'est un système qui existe, qui n'est pas trop affiché là.
Toi, tu trouves bien des choses comme ça. Non. Bon, bah écoute, on peut tout à l'heure.
Ben oui, j'ai quelque chose de finir. Bon, et après on verra, on essaie ou sinon on va manger quoi.
Là, il est quoi, 5 heures? Alors, l'hôtel, je demande une nuit plus, parce qu'il n'y a pas d'autre endroit.
Oui. Enfin, après, c'est déjà ça.
Oui, donc c'est
Ouais,
vraiment
c'est
une nuit
bien.
plus. Ouais.
Mais il faut que tu demandes, hein, parce que si on a de...
Je vais demander tout de suite.
Tu veux que j'appelle peut-être moi?
Ah oui, bonne idée.
Ah, non, c'est pas le même. C'est une chaîne d'hôtels, jamais donné le vrai numéro, ça. C'est. Алло, добрый вечер, Маргарита. Это говорит тут Андрей Родин из Института философии Академии наук. Знаете, вот один просто из наших гостей вот захотел еще на одну ночь остаться, вот за которую мы не платили, но он сам заплатит. Вот просто проверьте, пожалуйста, это вот. Да. Его зовут Марк Лашейзре, это номер 303 номер. Угу. Да, и вот ему, в общем, он в пятницу уезжает, 25-го. Да, еще на одну ночь. Угу. Нет, вот это он сам заплатит. Вот наши там уже, вот мы послали платю. Да, одну ночь. Одну ночь. Да. Угу. Ну, отлично, спасибо вам большое, спасибо. До свидания. C'est réglé.
Super, merci.
Mais il faut que tu payes pour une nuit.
D'accord. Mais tu as payé 5 ou 4?
5, je paye 5.
Ils prennent les cartes, je suppose.
Oui, je crois.
Je vais demander. Ok.
Donc, à 18h.
18h.
Ouais,
Je vais y aller.
D'accord. À tout de suite.
Merci encore.
Хорошо.